Hello, good evening, everybody.
Good evening, ma'am.
Okay.
Good evening, ma'am.
Good evening. Okay, so should we start? Can someone confirm if my screen is visible?
Yes, ma'am, your screen is
Yes,
visible.
ma'am.
Okay. So this week, the thing is, this week we will look into one more type of sorting algorithm, which is called quick sort. Last week we had discussed several other sorting techniques. This week we will look into one more sorting technique, which is quick sort. Then we will look into a small comparison between these sorting algorithms. Then we will look into a type of data structure called linked lists, stacks, and queues. And we look into something called hashing also. Okay. So to start with, let's begin with quicksort. So what quicksort is? So this is also, suppose, let's say, I'll just take a similar example as before. So let's say we have the numbers 5, 3, 2, 9, 4, 6, 1. Okay, let's say this is our given input, and we want to sort these numbers in the ascending order. Okay, so last week we had seen several other sorting techniques like this merge sort, selection sort, and all insertion sort, and all of that. So this time we will look into a slightly different style of a sorting technique. Suppose we have a suppose, let's say, what we will do is, what this thing does is, the quick sort algorithm, what it does is, let's say we will just start with picking one number from the start of the list. Okay. So let's assume, okay, we have decided that mutually that we will start picking the number from the start of the list. So we suppose we pick this number. So the start of the list is 5, the number contained is 5. So I will pick 5. And by some miracle, somebody tells me that this number 5 will go at the fifth. Okay, so I know that somebody has already told me that my number 5 will come over here. Okay, in the fifth place. So I will be having like four numbers before 5 and another five numbers after 5. Okay, I know that my 5 should come in the fifth place. How? We will discuss that after this. Okay, so what will happen is, once I know that my 5 will come at this fifth place, okay, what will happen now? All the numbers which are smaller than 5 should come in the part of the list, in the previous part of the list, and whatever numbers which are greater than 5, that should come after this fifth position, right?
Yes,
So every number which is after 5, I will pull it and put it in this part of the list. Okay, in the first part of the list before 5. Okay, so let's start. I have 3 here. So 3 is less than 5, so I will put 3. Then I see 2. 2 is also less than 5, so I will put 2 here. Then 9. 9 is greater than 5, so I will put 9 over here. Then I have 4. So I will put 4 over here. 4 is less than 5. So I bring 4 to the first part of the list. Then 6. 6 is greater than 5. So 6 will come to the right side of the list. Then 1 should come here. Then I have 8, 10, and 7. Right? So now notice that this part of the list contains every number which is less than 5. This part of the list contains number which is greater than 5, and all I have to do is recursively sort this part of the list and this part of the list using the same technique. Right? Is this part clear?
yes, ma'am.
Okay, so if that is clear, now we will discuss how we will know where to put this number 5. Okay, so for that, what I will do is I will have two uh, pointers. Okay, so the pointers here, sir has used the um, sir has used this L of J, L of lower, L of upper, all of that. Okay, so these are the positions. So what we will do is I will use this pointer. I will start from 3. Okay, I know that my 5 is greater than 3. Okay, so how I will put 5 in the fifth position? That is what I am discussing. Okay, so what I will do is I take this list and I will start checking from the second element. 3 is less than 5, so I will swap 3 and 5. Okay, so now my list becomes 3, 5, and then 2, 9, 4, 6, 1, 8, 10, 7, and so on. 8, 10, and 7. Okay, that's it. So then what I will do? I will take the next element, which is 2, okay, and I will check it with this particular, oh, sorry. I will not swap it right away. Okay, I will not swap it right away. What I will do is I will just keep checking it. Okay, so I have
Ma'am,
5, then
hello.
yeah, sorry, yes,
Ma'am, I have joined just now, ma'am. Are you teaching quick sort?
yes, I am teaching quick sort.
Okay, okay, okay.
So I will just explain once again what the idea is. In quick sort, let's say we discuss that we will pick the first element always. Okay, this is called as the pivot element. Okay, so I'm just picking the four. I'm saying that the first element is always the pivot. Okay, and so I will pick the first element, which is 5 in this particular example. And then by some miracle, suppose somebody tells me that 5 should come at the fifth position. Okay, so what I'll do is I'll put 5 at this position, and now what will happen? Every number which is less than 5 should come to the left of 5, and every number which is greater than 5 should come to the right of 5, right? So now all I have to do is recursively sort the left and the right of the left side of the list, left side of 5, and the list to the right side of 5. Okay, that is the idea behind quicksort. Okay, so now we are discussing how to know where to put this 5 and how to do this partition of these elements into these two parts. Okay, so what we will do is we will select a pivot, and we have already decided that the first element will always be the pivot. Okay, now what I will do, I'll start from this particular element. Okay, so now this element is less than 5. Okay, so I can just swap here. So I will have 3 comma 5. Six, 1, 2, 3, 7. Okay. Hello.
Yes, ma'am.
So now there is something. The thing that I'm getting confused is because of this notations a little bit. Okay, so never mind. Let's just go with this notation. Okay, so what we will do is we'll start from here. Okay, I know that this number is less than 5, 2 is again less than 5, but 9 is greater than 5, right? So my 5 should come between 2 and 9, right? So I can have, so every time I'm encountering a number which is less than 5, I can just swap 5 to the right part of it. Okay, so I will have, when I encounter 3, I will swap 5 over here. So I have 3, 5, 2, 9, 4, 6, 1, 8, 10, and 7. Okay. Now what I saw is 2 is coming. Okay. So now again 2 is less than 5. So 2 should come to the left of 5, and 5 should go to the right of 2. So I will just swap over here once again. So here I get 3, 2, 5, then 9, then 4, then 6, then 1, 8, 10, and 7. Okay. So now what will happen? I am coming across 9. Okay. So 9 is not less than equals to our pivot element here. Okay. This particular statement. L of j is here. Uh, 9. So this is no longer my pivot element. So what will I do? I will just skip this. I will not do anything else here. Okay, I'll just skip this element. I will go to here. Now 4 is less than my pivot element. Okay, can you give me 1 minute? Just give me 1 minute. Okay, hello.
Yes, ma'am.
Yeah. So now what we will do is I know my just give me 1 minute. I'm getting confused somehow. Okay. Just give me 1 minute. Something is confusing me right now. Here we do need two pointers. I was wrong here that we will be able to do with one pointer. We do need two pointers. The first pointer will be at the pivot element. Will point to the location of the pivot element. Okay, and the second pointer will iterate over the sequence of elements. So let's just start again. I'm very sorry for this confusion. Okay, let's just
No, it's
start
okay, ma'am.
once again. Okay. So let's say my pivot element I will be marking in green. So this is the location of my pivot element. So now what will happen is I will just start with my j will become this particular element which is the lower plus 1. So I will compare my jth element which is 3 with my 5 and I realize that my j is this 3 the number 3 is less than 5. Okay, so what will I do is I will so now the location of my pivot element should be at this position, right? So this
Yes.
position should be the location of my pivot element. That is what is done here. Okay, I is equal to I plus 1. So I become this should be the location of my pivot element. So now I have to just swap this particular value. So this will be the location of this particular element. So I don't need to swap 5 and 3. All I have to do is this, the first element will always be my pivot element. I'm not going to swap it here. I'm just marking at what position my pivot element should be there. Okay, so that is done here. After that, let's say we are going to 2, right? So when I am encountering 2, I know that my 2 is again less than 5. So my pivot element should be coming over here. Okay. So here will be my j and my pivot element will also be at this position. It will no longer be at this position. I know that there are at least two numbers before 5. So which are less than 5. So my that should be at least my 5 should be at least in the third position. Okay, so this will be the I know that this should be the position of my pivot element. Okay, so now what happens in the third scenario when j becomes 9? Okay, this position when j comes to 9, I know that 9 should not no there should be no changes because my pivot element should still be at the third position. 3 and 2 should come before the before 5. So if my 5 comes at the third position, my 3 and 2 can be accommodated here and 9 should come after 5. Right? This much is clear, right?
Yes, ma'am. Yes, ma'am.
Yeah. Now we go to the next case scenario when we have 4 here. So what will happen? My 4 should come before 9, right? And my pivot element should be here. It should no longer be here because I need to accommodate 4 before 5. So there will be 3 elements before 4, which means that 5 should be at least in the fourth position. So what will I do is I will increment this particular no, this pointer from this position to this position, right? So now my pointer should be at this, my pivot should be at this particular position. But here I am already having 9. 9 should not be here. All the elements which are less than 5 can be accommodated here. So I can just put 5 over here at the end, right? So what will I do is I will swap this 9 with 4. Okay, so finally, what will I get? I will have 5, 3, 2, 4, 9, then 6, then 1, 8, 10, 7. Okay, here my pivot element is still 5, and the position where my pivot element should come at the last, okay, will be the fourth position. Okay, I will just find where my pivot element should be inserted, right? So that is what I am doing. I
Yes.
am trying to find the position where my pivot element should be inserted. Simultaneously, I will also sort the list. I will separate the list into two parts such that all the elements which are less than the pivot element should come towards the come before this pointer, and all elements which are greater than 5 will come before after this pointer. Okay, that is what I am trying to do. So when I encountered 4 and I realized that 4 is less than 5, so my pointer should come at this, my pivot element should come over here, which indicates the position where the pivot element should be inserted. But I also know that my 4 is less than 5, so 4 should be in the left part of the list. So I have just swapped this 9 with 8. I hope this is clear. If you have any doubts, then please ask. Okay. So now,
Ma'am, ma'am, I
yes,
have a doubt. Ma'am, first, can you please clarify what is lower and upper here? Is lower my zeroth index and upper is the length minus one? Is it that so?
yes, at the beginning it is that. But when
Okay.
we are going recursively to these parts of the list, okay. So when I am
Mhm.
recursively sorting this part of the list, my lower will become
Mhm.
this and upper will become this.
Okay. And ma'am, when I tried this algorithm, I tried to run this program as well. I put the print statement in between and I was getting L of I and L of J, both are same. Like, I don't know what this eighth line is doing here. I'm not getting this eighth line.
Eighth line.
Yes, ma'am, I'm not getting. It looks
Here,
like it is
here.
swapping something, but I'm not getting because the values for L of I and L of J, it was appearing same. I took a list and I was checking like what is happening, but then L of I and L of J was coming same. Can you please
I'm
show
not
with this?
sure why you are getting the same, but what it is doing here is this particular scenario. When my I position I source the position where my pivot will be inserted should be there. With at what
So,
position
ma'am,
my
if
pivot
my
will be
pivot
there?
is I, if my pivot is I, then ma'am, this and J will be what? L of J
J
will be
is
what?
the position. J is the position. Like see here, I am incrementing J along this list, right? First of all, I started with 3, then I am going to 2, then 9,
So
then
my
so this is
then
the
at
counter.
very first position, my J will
Yes,
be L of J will be 3. You mean right?
yes, yes,
And
yes,
the 3 is less than pivot, right?
yes, yes.
Ma'am, it should increment I plus equal to 1. So my
Yeah.
will
So
be
my I comes over here to
ma'am.
this position.
Next step, it is saying L of I. That means it is 3, and L of J is also 3.
Exactly. Yes.
So that means there will not be any swapping.
Exactly. If there will be swapping,
That's
but
what
the
I'm
difference
saying.
will not
It
be
was.
visible.
That's what I was saying that when I was trying, it was coming same. So I'm not getting what is the use of this eighth line because L
That's
of I
what
and
I'm trying to explain.
okay, okay, yeah, I will wait.
So what let's say my I is over here at this instance, what happens is my I was at this position, right? At 2, right? Then I came across 4 and I realized that 4 is less than 5, right? So my I will be incremented, right? Which basically stores where the so here when I'm incrementing I, it is making sure that one more element can be accommodated in the left side of the list. Okay. So what is happening is when I'm incrementing I from here to here, these values are not there. My j is 4 now. Okay. I is at this position now. Okay. I was at this position. I was at 2. But now when I am when I'm coming across 4 and I realize that 4 is less than 5, what will happen here? I realize that I need to accommodate 4 in the left side of the list, right? Left of 5. So I cannot put 5 here because I am already having 2 elements. So I need one more element to be accommodated also. So I cannot put 5 here. Otherwise 4 cannot be accommodated, right? So I need to increment I by 1 so that I will be able to accommodate 4 among the first 3 positions. Is this clear why we are incrementing I by 1?
No,
Hello?
ma'am. No, ma'am.
Okay, see, what happens,
Ma'am,
suppose,
can you show it with the example or step by step?
yeah, that's what I will, okay, I'll do that. Okay, I'll do that. See, here we have 2. Let's say we don't have anything over here. Okay, let's just imagine this is the list. Okay, so when I'm coming across 4, my j is 4 here, and I have my I is 2. Okay, so I stores what? I stores the position at where I will be putting my pivot. Now suppose I do not change I at all. So what will happen when I put my pivot at this position? So now I'm saying that my fifth will go in the third position. Okay, let's put 5 at the third position. Then what will happen? My 3 and 2 can be, there are only 2 places before that, right? So, but there are 3 elements which are less than 5, 3, 2, and 4. So where will I accommodate the third element? I cannot accommodate the third element. There are 3 elements less than 5, but if I am putting 5 as the in the third position, then I will not be having space to accommodate all these 3 elements in the left side of the list. Are you able to get this? Is this clear? Hello? Hello? Can somebody confirm if this is making
Yeah,
sense?
ma'am. You are
Yeah,
audible,
ma'am,
but
you are audible.
Yes, ma'am.
No, that's not what I'm asking. I'm asking if this is making sense to you. If this is clear, why we are incrementing I?
yeah, ma'am. For me, it makes sense.
Hello, ma'am.
Yes.
Ma'am, could you write that what is the value of j and what is the value of I along
The
with
green ones is I. Green color is I. Green color is I. And this purple color is J.
Ma'am, if you
Okay.
increase the I,
Yeah.
then J will also increase. Then I and J will be
No, no, no,
same.
no. I'm not increasing J. J is
So,
my counter.
sorry.
All I'm saying is I have when I increased my counter to the to this index, okay? And I came across when I increased my J and I came across this fourth across the number 4. So I know that now I already had 2 elements which are less than 5. Now I have one more element and I need to accommodate that one more element also, which is less than 5. Okay, I have 3 elements now which are less than 5. So I need to accommodate 3 elements before 5, and hence my 5 cannot be in the third position. It has to be in the fourth position. That is all I am trying to explain. Is
ma'am,
this clear?
can we iterate according to the code for this list?
That is what I am doing actually. That is exactly what I am doing.
We are not getting that. That's what I'm saying.
Okay, so you want,
From I equal to 0 and like lower is 0 and upper is what 4.
okay, fine. Okay, fine. Okay. So we have the list is 5, 3, 2, 9, and 4. Okay. So what happens is we start with my I is the lower element. Pivot is the lower element. First of all, let's mark the pivot. Pivot will be equal to 5, right? Because we are taking the first element as my pivot. And why we are taking the first element as my pivot? Because I am saying so. That's all. Okay. There is no specific rule that we should always take the first element as the pivot. But now I am saying so that let's take the first element as the pivot. So we are taking the first element as the pivot. So let's just go with what happens. Let's just go with the first element as the pivot. And then we will discuss what happens when we change the pivot. Okay. So first of all, let us just assume that the first element is always the pivot. So this is my pivot. Okay. Now I will assign my I. I will start from the lower. Lower is this element, so this is my I. Okay. And my J will. So what exactly will I store? What is the idea behind I? I will store the position where the position of the pivot. Okay, like I told you here, right? By some miracle, somebody told me that my 5 should go in the 5th position here. I told you here, right? That is what my I will do. My I will tell me that hey, the your pivot, which is equal to 5, will go in the 5th position. That's the job of I. Okay.
So,
So
ma'am, in this case, I will be 0.
yes,
For
we are
for
starting.
and yeah, for easy understanding, I'm saying that for this case, we are considering it is starting from 0 position.
Starting from 0th position. Yes.
Yes.
Okay.
And
Then we
yeah.
will go from for J. So now in selection sort and in insertion sort and in merge, not in merge sort, in selection sort and in insertion sort, we had one particular variable which incremented over each of these values, and it went on counting, right? It just went on to the next number, checked where this number should be there, then goes to the next number and it does some checking and it does that, right? That is called a counter variable. Okay, so this is my J will act as a counter variable here. So what my J will do here is just increment and check for each of the numbers. Increment the index and check for each of the numbers. That is what my J will do here. Okay, so what I will do is I already know my 5 is my pivot, so I don't really need to check for it, right? So what I will do is I'll just start from the next index, which is my 3. Is this part clear? And
Yes,
what I will
ma'am.
Yes,
do is
ma'am.
I will just start from this position and I'll keep checking for until the last element, which is my 4. I will start from 3, I will check for 3, I will check for 2, then I will check for 9, and then I'll check for 4. Okay. Until the last index, I'll keep on checking for every element. So let's just start from 3. Okay. So when I'm encountering 3, what is happening when my J is at the at the first index, which is 3. Now 3 is less than 5, right? So I know that there is at least one element which is less than 5, right? So my pointer, the pivot, the variable I should capture this information that hey, there is one element which is less than 5, and hence there should be at least one position before 5. That means among these two elements, if I just take these two elements, then my 5 should come in the second position. Right or wrong?
Yes, ma'am. Right.
Right. So now what I will do, I will just increment itself to the next element. Is this clear?
Yes, ma'am.
Yes.
Right. So now what this is what the seventh line is doing. Okay. Now the eighth line. What the eighth line will do here? Eighth line will see that hey, every element before from 5 to this particular every element from this position, from the just after the first from the first position, from where we started checking till I should contain all the elements should be less than equal to 5. Sorry, less than 5. Okay, we are assuming that all the values are unique. Okay, all the numbers should be less than 5. We started from 3. and we are seeing that my pivot position is over here only. So there is exactly one element to check, and my this element is less than 5. So I am happy with it. Okay, I don't need to do anything else. So let's just skip over and go. So I don't have to do anything else now. So what I will do is I'll go to the next iteration. In the next iteration, what will happen? My j will count. My j will increment the index, and from 3 it will go to 2. Okay, so this is what a count. It's a counter variable. Okay, it is going to check for every number. So my j was checking for 3. The checking is done now. So let's go to the next element to check, and the next element to check is 2. Okay, so we will check for 2. So what happens now if I will check for 2? 2 is less than 5, right? Yes, 2 is less than 5. So earlier what I had, my pivot was at the first position. So it was saying that between these two elements, my I was the second largest element, and hence my I should go in the second position. But now among these three values, what is happening? Because my 2 is in less than 5, my I should capture that information. There are two numbers which are less than 5. Earlier there was one number which was less than 5. Now there is one more number which is less than 5. So there are two numbers which are less than 5, and hence it is not possible that my pivot element, which is 5, is the second largest element. Is it possible? It's not possible. There are two elements which is less than 5 already. So how will be my 5 will be the second largest element? My 5 is now the third largest element among these three numbers only. Does this make sense?
So ma'am, here the I will increment and then green pointer will go to 2.
Exactly.
Yeah, from
Exactly.
after that, I want to see what happens.
After that, yes.
Yeah.
After that, what happens now at this eighth line? At this eighth line, I need to ensure that every element before this particular green pointer should be less than 5. Okay, then only I can say that all of these elements are going to the left side of the list. Otherwise, I will have to recheck everything, right? So I need to ensure that all of these elements are less than 5. How many elements were there earlier? There was one element, but now there is one more element. So we are having like two elements now. I had already checked 3 earlier in the previous iteration. If you remember, we had encountered this 8th line and I had already checked 3. So I don't need to check for 3 again. What I need to do is I need to check for 2. I need to make sure that this element is also less than 5. Okay. So now I am doing that. 2 is less than 5. Yes. So I am saying that, okay, it is fine now. I don't have to do any more swapping. Okay. And then all this checking for 2 is done, and we can safely go to the next element. So now I'm just hold on for a little bit on what this checking is making sense. Why this checking is making sense? Why we need to do this checking? That will make sense a little bit after this. So just hold on for a little bit more. Okay. So all I'm saying is when I'm doing this check for 2, that hey, that 2, I had already checked until 3 in the previous iteration, and in this particular iteration I'm just going into this new element which is 2, and now 2 is less than 5. I have checked that, so we are on a safer side, and I can successfully claim that the elements which are previously which are on or before this particular index, okay, on or before this green arrow, the 3 and 2, okay, all of them are less than 5, and hence all of these elements can safely go into the left half of the list. Okay, that is all I'm saying. Okay, and why it is necessary, it will become clear a little bit later. Okay, so then now the checking is already done, so we will just skip to the next part. So my j will just see, done, 2 is done, so let's go to 9. So now my j goes to this index which stores the value 9. And now what I see, 9 is greater than 5. Okay, so I don't need to change my green index, right? Because I am already at the correct position. My in this new list, from 5 to 9, right? 5 is still the third largest element. 5 should go into the third position because there are two elements which are less than 5. 9 is greater than 5, so 9 should come after 5 or in the right part of the list. And my I should and my I is having the correct position where 5 should come. Is this making sense? Okay.
Yes, ma'am.
Okay. So
Ma'am,
now
so basically, we can say that I always points to the last element of lesser list, right? And J
last
keeps
element of lesser list. Yes.
checking whether this particular element should come inside the lesser list. If it is less, I mean, if it is lesser than pivot, then it should come and it increments I. And if it is not, then J continues moving, right?
Exactly. Exactly. Yes.
So, ma'am, here now I will not increment as the J is on 9. I will
Yes.
not increment.
No.
And that's why eighth line will not execute
No.
because that will not go inside the if, right? And
No.
then
It
the
will
J
not.
will increment.
Yes. So my J,
Okay.
what will happen after I increment J? It will remove from 9 and it will go to 4 now. Okay, this is where the catch starts, and this is where you will understand the exact role
Yes.
of the eighth line. Okay, so
Yeah.
now what happens again? My 4 is less than 5. So obviously, in this part of the list, I am having three elements which are less than 5. So my 5 cannot come in the third position, right? So my I increments itself to one more, okay, which is at 9. This position is currently having the value 9. I had ensured that until this, all of the elements are less than 5. But I had not ensured that this position can be anything, right? So now I need to ensure that I need to make sure that here my value, whatever value should be here, should also be less than 5. Then we can safely say that until this particular position, all elements are less than 5 and will go into the left part of the list.
So, ma'am, here now L of I and L of J will swap their positions. Like means 4 and
Exactly.
9 will swap their places.
Exactly. That is exactly what will happen.
And
That is the
okay.
role of the eighth statement. Okay. So what will happen here is now this list will be updated to 5, 3, 2, 4, and 9. My J was at this particular position and my I was at this particular position. All I did was swap their values. I did not change the counter. I just swapped the values at these two positions. So now I made sure that this particular position contains the value which is less than 5. Hence, this entire list, I can safely say now, this entire list will have contain values which are less than 5 and hence will go to the left part of the list.
But ma'am, here now the loop is already finished, right? The J loop already
Yes,
finished. Now it will execute
yes,
ninth line.
exactly. Yes.
So
So,
ma'am,
what is the
L of lower is 5 and L of I is 4 now.
yes?
So ma'am,
So, I'll
how?
just swap this two. I'll just swap this.
Okay. It
All
doesn't
I
matter the
said
left
is
side is sorted or not. It doesn't matter. But
doesn't
we have to
matter.
bring the 5 at its place.
Exactly. All
Okay.
I'm saying is my I told me that my 5, the pivot which has the value 5, my pivot will be in the fourth position of the list. So that is all I'm doing. I'm removing the element at the fourth position, putting this element over here. Now what I do with this element, I don't care. So I can just put 4 over here also. I don't really care about it. So I'll just put 4 here. Sorry, I should write in proper. Okay. I'll just put 4 here. Then I'll put 3, then 2, and then 5, and then 9. All I cared about is my 5 should go to the fourth position of the list, and I put it over there. My 5 is in the fourth position of the list. That's all I cared about. Now, and I did that. Now, what is the other thing that I cared about? Every element which is less than 5 should come into the left part of the list. and every element which is greater than 5 should come to the right half of the list. And that I also achieved. Right? All of these elements are less than 5 and all of these elements are greater than 5. Is this clear?
Yes, ma'am.
Yes, ma'am.
Ma'am, what is the
Yes.
role of pivot post in this quicksort?
Pivot is the element that we are selecting
No,
and we
no, no.
need to put it.
Not that, ma'am. The line number 15, a pivot post. This returning the ith element that is
Yes,
stored in the pivot post.
yes. So I will
Then
know
what it is?
from where to where. I will know from where to where is my left part of the list and from where to where is the right part of my list. I know my
Okay.
5, whatever my pivot was, it was the fifth element in the list. So I have put correctly the fifth element in the list. Okay. So now which will
Okay.
be my left half and which is my right half? I need to know that, right? So that is why
Okay.
I need my pivot position. This is the pivot position. So I know what is my pivot position. So my left half of the list will be this from lower to pivot position -1 and my right half of the list will be from pivot position +1 to upper.
So, ma'am, there is no rule that we can take any pivot number.
No, there is no rule. You can take any element as the pivot.
Okay.
But there is the catch here. See, the thing is, our target is to improve the complexity. Okay, let's just look into the complexity and then I come to the role of the pivot and which element should be the pivot. Okay, so what will be the time complexity of this algorithm? Let's say we are taking the pivot as the first element always. I'm claiming that my pivot element will always be the first element. Then uh, what will be the time complexity? Let's go with another color. So my time complexity, let's say I have an n-length list. Okay. So if I'm having an n-length list, my uh, my time complexity will be what is the time taken to do this particular partition? This is the partition, right? We are finding the position where the pivot should be there and where every other element should be placed, right? Whatever elements will be on the left half of the list and whatever elements will be on the right half of the list. And we are doing that in order of n time, right? Do you
Yes,
agree
ma'am.
with me that we are doing this in order of n time? Because
Yes.
all we are doing is we are just keeping our every element and we are checking where it should be there, what should be the values of the pointers and all of that. Okay. So if we take all of this checking and all of these swapping, all of these as unit operations, then we can safely say that I can do this partition in order of n time, right? Plus whatever will be the time taken to sort the left list plus the time taken to sort the right list, right? Time for the left list. This is basically size of left list plus the time taken for the size of the right list, right? Do you agree with me with this?
Ma'am, have you finished the
Yes.
code? I don't think it is finished yet.
It is done, right? I was discussing this
You
partition
just,
part.
yeah, just partition part. And ma'am, I don't understand why you are returning I then. What is the purpose of returning I?
The when we return I guess
Yes.
I discussed this quick sort beforehand. So what we are doing is my I is telling me my 5 should be at this fifth position or at whatever position. My
Okay.
pivot is at this position. So I know
Mm-hmm.
that all the elements before this pivot are less than this pivot value. All elements which are greater than pivot are on the
Mm-hmm.
right side. So all
Okay.
I have to do is recurse on each of these paths.
Recurse on this. Okay.
That is what this part of the code is doing.
Okay. So this is partition pivot underscore pause and then quick sort. This one, okay. But what is this doing? Partition pivot underscore pause. What is this doing?
Pivot underscore pos is basically the position where the pivot has been pivot is now currently lying. So what it means is I had my pivot as a first element of the list and now
Okay.
I have determined that my pivot is going to this particular position. the fifth
Okay.
position here. Okay, so I
Okay.
have
Because it
determined
is
that my
returning I. Yeah. So now my pivot
exactly,
underscore pos is I. This is
exactly,
I. Okay. So
yes.
this is
So this is
okay.
the
Then I
position
minus
that,
one. I minus one
yeah,
for the left side and I plus one for the right
right
side.
side,
Okay. 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 Got it.
right?
Mm-hmm.
Yeah. So now the time complexity will be order of n for this particular partition purposes. And then I am recursing on this left side of the list. So T of size of the left side plus T of the size number of elements on the right side. Number of element T of number of elements on left side plus T of number of elements on right side for the recursion purposes. Right? So suppose in some scenario I select a pivot such that while during every partition I will make sure that my number of elements are equally divided. Then what will happen? See, notice that this size is actually depends on the pivot now. The number of elements on the left side and the number of elements on the right side actually depends on the pivot. Is this clear exactly why it depends on the pivot?
Yes,
Because
ma'am.
of middle
Yes,
element.
ma'am.
Yes, if we take the middle element, the number of elements on the left side will be n by 2 and number of elements on the right side will be n by 2. If I am going to take the largest element, the number of elements on the left side will be 0. This is for the middle element. Okay. If I uh, if I take the largest element, then what will happen? My pivot is the largest element. So if I take my pivot as the largest element, the number of elements on the left side of the list will be n minus 1. And the number of elements on the right side will actually become 0. Okay. If I am taking the smallest element, then what will happen? Number of elements on the left side will become 0. Number of elements on the right side will become n minus 1. Similarly, if I take the second largest element, which I did over here, 5 was my second largest element in this particular norm. Okay. So then what will happen? Number of elements on the left side will become n minus 2. Number of elements on the right side will become 1. And so on. Okay. It depends actually on the pivot on how many elements will be there on the left side and on the right side. So what will happen is, suppose if my pivot always, I will choose a pivot. Somehow I am making sure that my pivot will always be the middle element. Then what will be my running time? This is the case 1. Okay. Pivot is always equal to the middle element. By some miracle, somebody told me, hey, somebody is coming and telling me, hey, choose this element. That is the middle element. You know that somebody is coming and telling you. So every time you are picking up the middle element because somebody is telling you that this is the middle element always. So what will you do? What will happen now? What will
Log n.
happen?
Now lists will be
Log
divided
n.
into two halves.
2t n by 2 plus order of
In
n, which will not be log n, it will be order of n log n.
yes,
Right? Now, suppose by some miracle, somebody will always come and he is telling you that, hey, this is the middle element, but he is cheating you and he is telling you always the largest element. Then what will happen?
then it will go two times. No, one will be t of n minus one, and other will
Order
be
of n
t of
square.
one.
Exactly. This will become order of n squared. Okay. Similarly, what will happen if you pick as your the smallest element as your pivot? Always.
Order of n square again.
Again, it will become order of n squared. Okay, so
Yes.
this is your best case and this is your worst case.
Excuse me, ma'am.
Yes.
Ma'am, can you explain again why you're adding the order of n in all three?
Order of n is coming for the partition purposes. Here we are partitioning. No, we are just going over every particular element and we are checking whether that particular element, whether I will increment I or not, and if I am incrementing I, whether I will swap these elements or not. All of those operations, that's checking the increment, all of those operations are taken as a unit constant time operation. So that is why the total time taken to perform this entire partition operation will be order of n. That is why we have this order of n thing. Okay?
Yes.
Yeah. Okay.
So
So this
my
is our best case, and this is our, yeah. Sorry. Yes, you were saying something.
so my base time will be that n log n. Yes.
Yes. Yes.
Okay.
Not n log n plus n, just n log n, right? Because plus will be.
Yeah. Order of n log n. Okay.
Yes, ma'am.
So now the scenario is, the question is, how do we determine the pivot? Okay, that's obviously we need to know, right? We should determine a pivot which will give me as close to n log n as possible, right? How do we determine that? See, the first thing is, we are having this order of n thing because we are taking the pivot as the first element, which is basically a unit time operation. We are fixing which element will be my pivot. So that is usually a unit time operation. But if this is taking if choosing the pivot is itself an order of n time operation, then what will be this particular time complexity? Can anybody guess that? What will be the time complexity if the time taken to choose the pivot? Every time I will choose the middle element. I'll find the maximum value, the minimum value, and I will find the value which is closest to max plus min by 2. Okay, I can do that, right? So it will give me an element which will be
Yes.
very, very close to the middle element, right? But in that scenario, what will be the time complexity of the partition?
N.
Order of 1.
No,
N.
order of n,
Order
order of
of
n.
n log n.
N.
No,
Just N.
No, n square, ma'am, because for
N
maximum
square,
also
I
it
think, ma'am.
has
N
to
square.
be traverse, right?
it has to traverse once for
Yes,
maximum, which is
yes,
order
and
of
then for
n.
minimum.
For minimum, it is traversing for order of n. Then
Okay.
again, it will find the element which is closest to that number, to the max plus min by 2, which is again order of n. Okay. Then the partition will be performed, which will again take me order of n. So it is actually order of n only. So what I'm trying to explain is, you can
Ma'am,
choose your pivot any way you like, but please make sure that the choosing of the pivot should not exceed this order of n time complexity. If you are choosing the pivot such that it is taking order of n squared, then what will happen? This particular term will become n squared, order of n squared. Then everything will go messed up. But if you are choosing the pivot such that the choice of the pivot is limited by order of n time, then it will no longer be effective. It will not affect much. Okay?
okay, ma'am, got it.
Yes. Any questions? You were asking, somebody was asking something.
No, ma'am, it's clear. I was asking that.
Okay.
Ma'am,
Okay. Yes.
could you please just little elaborate that Tn equals to 2t n by 2?
Okay, sure. So here we have this thing you understood, right? This particular equation.
Yes, ma'am.
So if this particular equation is done, I am telling you the middle element. By some miracle, somebody is coming you and telling you that, hey, this element will be the middle element, so you pick this element. So what will be the size of the left list every time? During every iteration, I am telling you this will be your middle element. So during every iteration, if you are having an end list, I told you that this will be your middle element, then what will happen? This will become T of n by 2, right?
Okay, okay, yes, yes, yes.
And the right side will again become T of n by 2.
N by 2.
Because I told you, hey, this is the middle element, pick this element. You are picking that
Hmm.
element and you obviously put it in the middle,
Yes,
of course.
then both are the half half.
Yeah, so both of them becomes half of it. So T of n by 2 plus T of n by 2 plus order of n.
Okay, yes, got that.
Got it?
Ma'am, I just have a doubt. Order of n is
Yes.
supposed to be worst case compared to n log n, isn't it?
No, n log n is worse than order of n.
Okay.
Order of n. What I'm saying is, if your time complexity is f of n is equal to order of n, and g of n is equal to order of n log n, okay,
Okay.
then f of n is equal to order of g of n. You agree with this, right?
Ma'am,
N
N
will
log
Yes.
be
n
Ma'am.
is greater than On, isn't it?
yeah, n log n is greater than O of n. That is
Yes,
what
yes. Okay, okay.
n log n is greater than n. That is what I say. It's clear, right?
Yes, ma'am. Yes.
Yes,
Okay.
ma'am.
Yes, ma'am.
Okay. Any other doubts?
Ma'am, can you explain what you wrote above? On plus On plus
No,
four
no, no.
times.
That was for just one
Yeah.
particular example when computing the when like we have made a new rule. Like instead of selecting the first element as the pivot, we will find the maximum element in the list. We'll find the minimum element in the list, and we'll choose the element which is closest to max plus min by 2 as my pivot. If we are doing that as the rule, then what will be the time of this total partition function? For that, I was calculating here. Choosing the maximum element is order of n. Choosing the minimum element is order of n. You find order of max plus min by 2 in constant time, which is order of 1. Okay, here there will be another order of 1. Then I am going to find the element which is closest to that particular value. That will take order of n. Okay, and then the partition. So now I know which element will be my pivot. So I know this pivot and I'll just divide into two parts, perform this entire partition procedure. So that will be again another order.
Yes,
That's what I
then
do.
this will prevent the worst case, n square complex.
This will bring you very, very close to this particular case.
Yes, ma'am.
Okay. Yeah. Okay. If there are no other
Ma'am,
doubts, then let's. Yes.
ma'am, in the recursive call of the function of the code, ma'am, it was given that pivot position -1. So when we perform the code, it won't take the two elements before the pivot element.
Sorry. What you're saying? Yeah.
Here it is given, ma'am, pivot position -1.
Okay.
So it won't take the two elements before the pivot element. Like when it,
No, 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 no. Upper is my pivot position -1. I'm not saying that my length of the string is pivot position -1. I'm saying that my upper limit of the list is going to be pivot position -1. The highest index of the list. Upper
okay,
stores the maximum index of the list.
okay, ma'am.
Yeah. If I am having a n length list, okay, then my lower will be 0, upper will be n minus 1. Lower and upper stores the indices of the starting index of the list and the ending index of the list. Okay. Hello.
Yes, ma'am.
Yeah. Is that clear or any doubts?
No, I'm clear.
Okay. So let's go to the next part. So this is the best case time complexity we discussed. The worst case we discussed. For the average case, it is basically an average of what happens most of the time. Sometimes we get n by 2, sometimes we get n, and so on. So this will approximately will give you order of n log n. This Detailed analysis of the average case time complexity is beyond the scope of this course. So you can just get an idea, right? Sometimes it is equally divided. Sometimes it is mostly it is skewed, like one side is larger as compared to the other side, and in the next iteration, the other side is larger than this side. So on an average, it will come back to order of n log n. It will be slightly larger. The constants may be slightly larger as compared to the best case scenario, but it will come back overally. If you look into the asymptotic time complexity scenario, it will become order of n log. Okay. So now sort in place, yes, it is true because we are not creating any new array to sort this particular to sort the given list, unlike the merge sorts, right? Recall in merge sort we needed a new array to sort the elements to perform the merging operation, right? So that is why merge sort was not an in-place sorting, but quick sort is actually an in-place sorting, because here we can just sort here and there only by swapping a bunch of elements here and there. Okay, and then now notice that it is not a stable sort also. Why? Because recall that we had three here. We had okay, recall that there was 3 and then 4. While we are swapping, we are not making sure that we are just ensuring the order in which the values are there, right? We don't need to ensure the order in which the values are there. With this particular implementation, we are not ensuring that the order in which the values have occurred are still there. Rather, we are just saying that we are just swapping these numbers and we don't care that which came first and which came last. Okay, that is why it is not a stable sorting algorithm. This is a table which shows the best case, average case, worst case of all of these different algorithms that we have discussed. Okay, so notice that merge sort is not an in-place sorting, but it is a stable sort, and the best case, average case, and worst case running time is order of n log n. For quick sort, the best case and average case is n log n, but the worst case is n squared, which is really bad. Okay, although it is an in-place sorting, but it is not a stable sorting. The
Ma'am, what is
interesting
in
thing is,
place actually? In place means?
in place means we are not creating any more arrays. We are not creating any new lists or any new arrays to store the values or something. Recall in
Okay,
merge sort, while merging, we used to create one new array and then we perform the merging operation.
okay, ma'am.
Yes. So merge sort was not an in-place sorting. Quick sort is an in-place sorting. Insertion sort and selection sorts are also in-place sorting algorithms. Okay.
Ma'am,
So
sorry, ma'am. Stable means what, ma'am? I didn't understand properly.
So stable, what happens is, if you recall the last week's session, we had discussed this. Suppose there are two people with the same name, let's say Rahul or Ajay or somebody, two people with the same name have joined in the course, okay? So both of them are having the same name, but their roll numbers are different now, right? So one of them is having one with one number and the second one is having second number. So let's say Rahul one who came first, Rahul who came first, I have assigned a ID of 25 to this Rahul, okay?
Okay.
And then I have another Rahul, which is the second Rahul, who is having the value 12.
Okay.
Okay, so when I'm sorting these Rahuls, or when I'm sorting according to the names or something, if this Rahul comes first and then this Rahul comes second, then it is called a stable sort. But if this order is has been changed, if this doesn't occur according to this particular ordering, no, then it is not a stable sort. Any place if it has changed, then it is no longer a stable sort. So suppose I have 25, then there are some numbers before 25, there are some numbers, then there are some numbers, then I have 25, then there are some numbers, there is another 25. Here there is another 25. Okay, so let's mark these 25 with different colors. So this is 125, this is another 25, the yellow color is another 25, and green color is the last 25. Okay. So when sorting, once I sort these numbers, if I know that the 25 with this blue color comes first, then there will be the 25 with this purple color, then the 25 with yellow color, and then the 25 with the green color, then it is a stable sort. In any other form of ordering, it is not a stable sort. Okay?
Okay, so I understand this, ma'am. Thank you, ma'am. But how do you say that quicksort is not stable? Because I'm only sorting from the perspective of the pivot. So from the
Yes.
pivot perspective, whatever is on the left is lesser than that only, right? So it should be safe.
Yes. See, let's see this thing. Suppose I am having 10 twice. I'm having 10. I was having 5 here. Okay.
Huh.
5, 10, 5. Then I am having 2, 3. And then I am having 6, 8, and 5. Okay.
Okay.
So what will happen? I will get 2, 3. And then can you ensure that this
Oh,
5
okay.
will
Which
come
five
out?
came first? I got it, ma'am. I got it. Whether the zero five is coming or the second five is
First
coming.
5 is coming.
Ah, got
That
it.
we don't know,
Right.
right?
Okay, got it. Got it. Yeah. Thank you, ma'am.
That's it. Okay.
Ma'am,
Yes.
ma'am, why the quick sort is preferred over the mud sort? Even the worst case of the quick sort is more than the like mud sort. So why then also it is preferred?
I can't say that it is preferred, but in general, if you pick the pivot very carefully, no, then you can make sure that the worst case will come very rarely. That's one.
Actually, ma'am, in the lecture, sir was saying that the quick sort is more like preferred over the merge sort, and it is used as built-in sort methods also.
Yeah, it is built in short methods, but they are using very intelligent techniques to guess the pivot. And while they are simultaneously controlling the running time to find the pivot. Okay, so that is why they are like higher level implementations, like it depends on the choice of the pivot. For quick sort, for merge sort, you just have it, you just know that this is order of n log n, this will be order of n log n, you know that. But for quick sort, and simultaneously, whenever for these packages, what happens is, when you are like running for very very large numbers, there will be some applications. You may, let's say for example, in astrophysics or something, you are running these positions of the stars, you're shorting the positions of the stars, there are infinite number of stars. Okay, and you're taking a that list will be very very large, right? So when it is not an in place sorting, no, you will need to create one more list of that sort. You will have to create another list which will store that very very large number of elements. But in quicksort, you can just do with that one particular list. Secondly, if you are just trying to control the choice of the pivot, or if somehow you can control the choice of the pivot, somehow you just make sure that pivot has been controlled perfectly, then you can ensure that the running time will always be order of n log. Somehow, if you have that control over that pivot, right? So that is why these implementations are very higher level implementations, where they use there are these the actually, if when you are going to learn about, if you are learning about randomized quicksort algorithms, which is basically you pick a pivot randomly without just looking into anything, you just choose some random number and pick the pivot, then also you can ensure that your running time will be order of n log. Okay, in that scenario, most of the scenarios, you will get a time complexity of order of n log n, and simultaneously you are also getting an advantage over the space complexity, because you don't have to create another array of length n to perform this sorting, right? So that's why quick sort is preferred over merge sort for these higher level implementations and everything. But if you are looking into a very low level implementation, like you want to sort like 10 numbers or something, okay, then you should go for some simpler sorting techniques.
Okay, ma'am.
Yeah.
Ma'am,
Yes.
ma'am, we say that merge sort is not in place because in that merging function, we
Yes.
take a third list C and append it. So that is why it's
Yes. Yes. Yes.
okay, ma'am.
Okay. So once this is done, let's go to the next part, which is basically a new data structure called linked list. Okay. So what happens is, okay, so there are two different things. In Python, we have something called as a list. Okay. That list is basically denotes an array. It is an array. Okay. Array of numbers. Now, this linked list, this is not equivalent to the Python's list thing. The Python list, which is the looks something like this. Okay, this and this list and this list are completely different things. Okay, so this linked list is basically a data structure, just like arrays and arrays. This linked list is a data structure, but the list function or the list variable that is used in Python, that is basically a name for arrays. Okay, in Python, whatever lists we have, no, let's say L is equal to 1, 2, 3, 4. All of this denotes an array. This is an array. Okay, this is not a linked list. This is an array. Okay, so here the name of the array in Python is list. Okay, it is not a linked list, it is an array. The name is it's just called as list. Okay, but what we will be looking into now is called as linked list, which is basically a new data structure. Okay, so until we are learning about linked list, I will be whenever I'll be using the term list, I will be referring to linked list and not to the Python list. Okay, so Python list I will refer by the name of array, and linked list will be about and the name list or linked list will be used to denote this new data structure that we will be discussing. Okay, so until only for this particular portion, okay, until this linked list part is covered. So now what linked list is, so what happens is when in an array we are given a list of numbers. Okay, we are having some numbers in an array. Let's say we are given this 2, 3, 4, 5, and all of that. So what we will do is we want to, all of them are friends, and when we want to store some memory location, or we will store this in the memory, all of these numbers in the memory. What an array does is it finds contiguous memory locations. So what happens? There will be a one continuous locations, the list of continuous set of locations which are empty. It will find that kind of a memory, and I will take this complete set of numbers and I'll put it over here. 2, 3, 4, 5, 6, 7, and so on. Imagine it like in a class, you are a bunch of friends and you want to sit together. Okay, so what you do, you just sit together in one particular row or in one particular bench. That is what you find, a bench which is completely empty, and you go there and you sit. Okay, that is what an array is. But what a linked list is something different. What it does is, every one of you, there is no particular one single bench which is empty. So all of you can't just get into that one particular bench. So what you do is you randomly sit across the hall. And what happens? One of you, the first person, knows where the second person is sitting. The second person knows where the third person is sitting. The third person knows where the fourth person is sitting, and so on. This is what is called as a linked list. So what happens in this data structure is we have a set of numbers. We allocate one particular random memory location to store that one particular number, but every number will store the index or the position, the memory position where the next consecutive number is present. Okay, so I have 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, I am given these 6 numbers. You are 6 friends, and you have numbered yourself as 1, 2, 3, 4, 5, 6. Now, if you find a bench which is completely empty, and all of you sit like 1, 2, 3, 4, 5, and then 6. This is called as an array representation. Okay. But the other representation is I put 1 over here in this particular memory location, 2 is in some other memory location, 3 is in some other memory location, 4 is over here, 5 is over here, and 6 is over here. Now, what one does, it starts making some little bit of intelligent thing, and what one does is it stores the number of where the second one is. The memory location where 2 is present. 2 stores the memory location where 3 is present. 3 stores the memory location where 4 is present. 4 stores the memory location where 5 is present. And 5 stores the memory location where 6 is present. Now, how do I know where 1 is present? There is one particular chit somewhere which is called as the head chit or the head or something, and that stores the memory position where 1 is present. Okay. These these things are called as pointers or reference pointers. Okay. So the head is a pointer which stores the memory location of the first element. The first element stores the memory location. The first element, the node containing the position or the node containing the first element will also store the position for the second element. The node containing the second element will also store the position for the third element. The node containing the third element will also store the position for the fourth element. The node containing the fourth element will also store the position for the fifth element, and so on. Okay, until the last element, which doesn't have any position to store. So that location where it was supposed to store a position, it will have null. Is this clear?
Yes, ma'am.
Ma'am, please repeat again.
Yes. Okay. So we have a head position. There is a chit called head where it is written where 1 is present. Okay. Now in 1, what will happen? At this particular position, 1 will be seated and there will be a chit containing the position of the second, where the second friend is present. Okay, I'm going to the friend example again. Okay, there is a note on the board which is writing the head, which is called as the head, and it is writing, hey, 1 is present at the location number, at bench number this, position at row number this, column number this. Okay, head is storing that. Now, what 1 is storing? Where 1 is that? It is sitting there, and on the bench it is writing. There is one note with 1. There is a chit sheet kind of sheet with 1, which is storing the position where 2 is present. Now 2, it is present at one particular position, and it is also having the chit sheet with it, which is storing the position where 3 is present. Now what 3 is doing? 3 is sitting at one particular bench, and it is also having the chit sheet which stores the position where 4 is seated, and so on. So now the last person, it doesn't have anybody's position to store with itself. So what it does is it just writes null in its cheat sheet. That's all. Simple thing.
Oh, okay, I got it. That means the last element will not have any kind of cheat because it's the last element.
It will have a cheat which will contain the value null.
Okay.
Okay. So every position we will store 2 information. One, what is the value which is indicating the particular person, and another will be called as the reference pointer. Okay, which is basically the chit sheet containing the position of the next element. Okay, this is coming back to the
Position means
numbers.
the place in memory, right?
Exactly, the place in memory, the location, memory location.
Ma'am, is this the linked list is just similar like the B plus tree linked list? Means we have done B plus tree in DBMS, so in there also we have learned about linked list. So in
Yeah, it
that case
is
also.
somewhat similar. You can say it is somewhat similar.
Okay, got it.
Ma'am?
That is basically in B plus tree, you are using the linked list. You
Yeah,
are
that is all
using
I'm
the
telling.
data. That's what yeah. B plus
Okay,
tree, you are
okay.
using a linked list.
Yes, yes, that's what I'm telling.
That's
Yeah.
an
Okay.
application of linked list. Yeah.
Okay, okay.
Sorry, ma'am. One doubt. Actually,
Yeah.
let's assume there is no one in a room.
Okay.
So is it possible there is some head or what? And if the head are there, so what the data he have?
Head will store the position of the first element, the memory location of the
No,
first
yeah,
element.
yeah, but let's assume there is no in a room. But means there is nothing in list.
Yeah.
Nothing. So
Head will
is
be
it
equal to null.
okay? So so the head are there, huh?
Sorry?
So the head are there. We have to make a head always.
Yes.
It is
A
doesn't
list is
matter
defined.
someone are in room or not.
Yeah, the value of the head determines the name of the list.
Okay. So head is store what? Like head is just like a node, na?
Head is
So
just
it
like a node.
head is a node, the first
Head
node,
is
na?
a node. Yeah, head is a
Yeah.
node for which the value will be none. Okay.
Uh-huh.
And the reference pointer will be the position of the first element. And if there are no elements in the list, it will have null.
Oh my God. Yeah. Thank you.
Okay. This is clear?
Ma'am,
Yeah, I got it
position
actually.
pointer means the index.
Sorry?
Position pointer means the index of that
Not
element.
the index, the pointer means the memory location of the next element. Memory location where the next element is present.
Ma'am, can you show example?
Okay, so in an example, I exactly don't know what the memory positions are there in a like what the memory locations are there in the memory. So let's say in our computer memory. So let's say that our computer memory is numbered from 0 to 64 or something. Okay, our computer memory is denoted from 0 to 64. I have five elements: 5, 2, 3, 1. Sorry, let's say I am having just five elements: 1, 2, 3, 4, 5. Okay, or let's say A, B, C, D. Okay, this will be easier. Okay, so now I am going to insert. I create a new list and I set my head. Hello head. Store the value none and the value null here. Why? Because I haven't yet, none of the students have come here. There are no values now. So just store none and null. Okay. So now what happens? A is coming. Okay. I am trying to insert A. So what will happen? I am trying to create a list and I want to put in A. So what will I do? I will just find a position in memory which is empty. I'll just choose some random position. Let's say I'm choosing the position 12 and I'm writing A over here. Okay, so now what head will do is, at this it will erase this null. It will take a pointer to this 12th position. So what it will do is here, instead of like putting this pointer, what it will do here is it will write 12 over here, which will mean that my first element, which is A, is present at the 12th position. Now, A, what it will do is, in its shift seat or its pointer, whatever you want to like to call, here it will have the value null. Right? Now, one more element is coming. Let's say B is entering now. So what I will do is, I'll choose some random position in the memory which is empty and I will put in B. Let's say I'm choosing the value 64. I'm choosing the last number. Okay. I'm choosing 64 to store B. This is the memory location containing set 64 and it stores B. Okay. So what A will do is, A will just erase this null and it will store the value 64 here in its chipset. And what B will do is, B will store null over here. Then C is coming. Okay, so now I will find some particular random memory location which is empty. Let's say my fifth index is empty. fifth position in the memory is empty. My memory location number 5 is empty. So I will put C over here, okay? And I will allot the value null over here, okay? But I will change my B, the chipset of B or the pointer, the reference pointer of B will now be updated to store the value 5 because the next element which occurs after B, the element which occurs after B, which is named as C, the value C, it's the element which is after B, okay? That is at position number 5. So I am putting 5 over here. Is this clear or do you want me to continue?
Yes, ma'am, it's clear.
Okay.
Means we are initializing with null, and then as the values are coming, we are putting that position.
Exactly, yes.
Okay. So
Ma'am, I
last
have a doubt.
last
Yes.
element will not change the null value.
It will skip storing the value as null.
Okay, okay.
Yes. Actually, null is basically a general thing. It can be none. In Python, we use the term null. It's not null, it's null. Okay.
Ma'am, my doubt is in Python there is, I think there is not a concept of pointer. Then what we will do for it referencing?
See, for that we are supposed to create a node. Here, if you look into the actual implementation of linked list, here we are creating a class called node, which is going to store a value and it will have a next pointer which stores the none here. Okay. So when we are creating one more value, what we are doing is we are updating the values of the previous node. Temp.next contains node of B. So it will store the position of the object. Okay, so that is using classes and objects we are doing this in Python. Okay, so what happens
Ma'am,
in Python? We are creating the object of the node class. Okay, this object will store a value which was the A, B, C, D that we had, and a pointer which was initially storing none. Okay. Now when I'm creating one more, when another value is coming, it was initially, let's say this is A. Okay. Now when another value is coming, so that will be having the number B. Okay. And I will have this none over here. Now A dot next. This is called next in this particular reference pointer. The name of this pointer is called next. Okay, the value is a. The next pointer, the value of this next will be equal to this particular object. Now, what will be this? When I say that this is equal to node of this, when I'm saying that this, okay, node of B, this will basically what it will do is it will allocate the position of the next element, the position of the object in the next of the next object, the position in the memory location that it will come and store. Is that making
Ma'am,
sense?
then how can we differ with the node and its pointing? Like, because like in C++ or any other language, we use a star mark to point that this is a pointer. But in
Yeah.
Python, how can we mark it as a pointer?
See, we are using this next as a pointer. This next variable, we are just using it as a pointer. Instead of storing some particular 1, 2, 3, 4 values, we are storing the location of the object. We are appending it with the value of the node of B. We are appending this with node of B. So what node of B is basically, it is creating one more object for the which stores the value B.
Ma'am, there is no need to declare it as a pointer initially.
No, we don't really need to declare that this is a pointer. This is another variable, but we are using it as a pointer. Okay.
Ma'am, I'm sorry, ma'am. How you are telling that next is the pointer, ma'am? That is get confused.
See, next is storing node of B. Here we are making sure that we are saying that self.next is equal to node of B. Okay, so what will it store then? What is node of B? Node of B is basically we are creating an object of the class node and such that the value will have value. There will be two variables, one is value and another is next. This is an object of the class node, and the value of the value will have the value, the variable value will have the value v, and next will store none. Right? This is how this class has been defined if you look into it.
Yes, got it.
Right? So
Yeah.
when I'm creating this, when I'm writing node of V, then it will just create this particular node. And when I'm saying that next, self dot next is this next, something, not next of that particular node, temp dot next here. Okay?
Mm-hmm.
That means whatever is the temp node, temp variable is pointing to. Okay, whatever temp object the temp variable is pointing to, the next variable of that particular object. So what temp here is? Temp here is another object of the same class. Okay, this is temp. It's
Got
named
it.
as temp. So its next value variable will store this particular object, which means that it
So,
will store the memory location of this object.
no. The confusion, ma'am. In temp, in the next of temp, it will have
Yeah.
v and none, both of it, right? Because it is
No, it
storing.
will not have v and none. It will have the object of the class node, which stores the value v for the variable value and none for the variable next.
So it will store the object of that node.
Exactly, yes.
And
But
from that, I can get object dot v and object dot next also, right?
exactly,
Okay, I got
exactly,
it.
yes.
I got it, ma'am. Thanks. Yeah.
Ma'am,
Ma'am, can you?
hello. Hello, ma'am.
Yes, yes.
Yeah, I have a one doubt. Actually, if our agenda is making a node, then why we defining such kind of function like insert, delete, and like we can by just class node and putting some function, we can define the node and putting all the functions which is delete, insert, and the other classes which is the linked list. This is like
This is
copy and the code is very long. Then
I get it, but this is basically a definition of the linked list data structure. Okay, so in a linked list data structure, we want to append a node to the end of the linked list. We want to append insert a node to at the start of the list, or we want to we want to delete some particular node. These are functions which perform that.
yeah,
When I'm
but this
saying head is equal to node of 10, which means that I am starting a linked list which has been named as head, and the first element is 10. Okay, so that is what it means, like head is a linked list here. So all the functions of the linked list have been contained in this particular class, which stores whose object is basically defined as the one particular node of that particular linked list.
okay,
That is
because
valid.
I'm saying because of class node I'm mixing with the linked list function because if, we can also do like making the class node on the separate cell and making the linked list class on the separate cell. So it's better because when we calling the node, then node make, and when we calling the linked list, then the function of the linked list all called.
Sorry, I'm
That's
not
better.
getting your question. I'm not getting your question.
It's not a question. It's just like making the code better because when we designing the code just like that, making the class on a node just like that, we have a Jupyter node. So there are a lot of the cells. So we can make the node on the one cell and then all the other things like linked list function like append, insert, and everything we can define on the different cell of the classes which is called class linked list, and then because the code is like look like it's like we are defining some class node. So when we calling the class node, then what class node like it's appending something. It's like good code.
See, what happens
Just,
here? See, what you are saying is you can just define a separate functions for each of these particular functionalities, right? See, what happens here is I have a head node which is basically defining my linked list. Okay. Now, when I am saying there is one more linked list which is head one. Okay. So what head not head of one. This is head capital H1, and there is another linked list called capital H2. Okay, there is another linked list called capital H3. each of these points to the three head nodes of the three linked lists. Okay. So now when I'm saying that insert a particular node to the first linked list, which means what? You have to perform the insert operation for this particular linked list called head one. Okay. So yes, logically, when you write a function separately, insert to what particular head of the linked list, and then you perform this entire operation, it is true, it is correct only. It is not wrong. But here, what we have given here in this code, this is basically the definition of the linked list. Okay, here we are defining a linked list as a collection of these nodes. So every one of those nodes should be able to perform that operation. What we are saying is, when we are inserting a node, my head should also be able to, the head should be able to, this is my linked list. My linked list is head one. So my head one is now performing this operation, the insertion operation. I am not doing the insertion operation. The linked list is doing the insertion operation. That is why when we write things like head1 dot insert, okay, this means what? I am not calling the insert operation. H1 is calling the insert operation, and it is inserting some value in that linked list, in its own linked list. Okay, but what this means is insert the value v to h1. This means what? I am performing this insertion operation to h1. Okay. Technically, what you are saying is correct. Logically, it is also correct. But from a data structure point of view, when you are trying to understand what the abstractness comes here, the data structure, we are saying we are trying to say that this data structure is able to perform all of these operations by doing this. You get it? And secondly,
Yeah.
this code is the pseudocode that's been given here is just for reference purposes. Like for example, here we have given the code for delete, but there are two different functions here. One is the recursive function. One is sorry for append here. You can see this is a recursive function for recursive definition for append, and this is an iterative way of performing the append operation. Okay, so these are just for references. You don't have to just copy paste the entire code and use it. What we are given here is just for reference purpose, so you understand what is happening, what is being done, and you write your own code. That's the idea. Okay.
Ma'am, can you please once again explain what is happening from while defining the node?
Okay, while defining the node, what I'm trying to say is, we are showing that we are putting all of these functions inside the node, so that we can say that these are the functionalities of the linked list. Instead of creating separate insert functions, which may be called by some other things also, some other data structures also, instead of doing that, we are putting that in this one particular definition of this class, so as to make sure that these are the functions of a linked list data structure only, for this particular linked list data structure only, and hence this operation can be performed only by an object of this particular linked list data structure. That's all I'm trying to say.
Okay.
Okay.
And ma'am, what is stamp is storing?
Sorry?
What is stamp is storing? TMP.
Temp. Oh, you just
Yes.
need to look into this. Temp is kind of performing a counter kind of thing, just like we use the J in the quicksort. No, it's doing something like that. You need to look into this code. Just try to understand the pseudocode, what is happening and not. If you're having any doubts, then you can post and disclose or something. Okay.
Ma'am, I have two doubts here.
Temp here is mostly working as the J that was working in the quicksort. Just going to the next element and looking, checking. That's the thing. Yeah.
Ma'am, temp
Somebody
is
has no
equated
doubts.
to self.
Sorry?
Why does ma'am temp is equated to self? Why does it so?
Self means whatever node of the class which has invoked this particular function. So if I'm writing h1 dot insert, which means that temp will now be equal to h1. whatever value the h1 is storing. Okay, it
Okay.
will not be
Okay.
equal to h2. Okay, self here means that the object which is invoking this particular function.
Yes.
Yes, somebody
My,
has two
my
questions.
first doubt is when we are declaring any node, then we are
Okay,
passing the whole node to the next. Hence, the
yes.
next will contain the whole node, not the address of the node. Uh,
No, see, when we are passing the node as a function, it is basically an object. So it will become a reference pointer. It will actually store the address of the node.
no,
It won't be able to store like the entire. See, what exactly my next is holding? Next is holding an object of the data structure of the class node, right?
yes, ma'am.
It is holding an object of the class node. My class node something looks like this. B, and here there is none, right? So now when I am putting this inside another object, will it look like this or something? Are you saying it will look like this?
Yes,
This
ma'am.
will
Yes, ma'am.
be
I am exactly saying it is doing this, not to the linked list like thing.
it's fine. Why don't you implement it and check what it is storing? Because see, what I'm saying is it won't be able to store the entire object. This object, it need not hold just two values, right? One, V2 and none. For this particular example, it is having just two values. One is the value and the none. It may be having like student information. All the information of a student is in one particular box, like the name of the student, the roll number of the student, his father's number, his mobile number, his mother's name, his Aadhaar card number, his address details, his contact numbers. All of that information can go into just one particular object, right?
Yes,
It
ma'am.
will not. How will it just keep on putting one object inside another object?
Ma'am, here we are doing the same thing, na? We are putting the
We are
whole
not doing
object.
that. We
We
are
are
not
putting.
doing that. We are just assigning that value. What value are we assigning? When it is an object, what value are we assigning?
Ma'am, but we
And we are
are.
saying temp dot next is equal to node v.
Yeah.
Yeah.
Then temp then next will contain the whole node, na? Iska, the meaning of the this
And
line is the same. We are putting the node as a value of the next.
when I'm writing b is equal to 5, what exactly is happening here?
Ma'am, we are putting 5 value in the v, not putting reference of 5 in v.
No, what is happening here is there is a memory location which stores the number 5, okay? And now this memory location will be referenced by the name B. That is what is happening here. When we are writing B is equal to 5, that is exactly what is happening here. There is a memory location which stores the number 5 in some memory location XIV, let's say some memory location A0001F. This is some memory location called this, and that particular memory location is storing the value 5. Now, I don't know this particular memory location. So what I'm doing is I'm just assigning this value name V to reference this particular memory location. I'm renaming this memory location to the value V.
The
Okay.
same thing
So
is
there
happening
are
for the node.
yeah, wait, just I'm coming to that. So there are different types of these reference pointers. There are different types of how we assign this. It may be the scenario that we have one particular position which stores, which has been, this is a particular memory location which has been, this is let's say B00X E2 or something like that. And this is storing this particular memory location. That is also possible. Okay. When I'm saying this, I'm referencing this as B. I'm renaming this as B. So that what we will do, V dot something will become 5. Something of that sort. This is what is called as a pointer. If you look into C, if you have read C, you must know about these pointers about this thing. So what it does is there are different ways of pointing to one particular memory location. That is exactly what is happening. When I'm saying V is equal to 5, it doesn't mean that it is creating some V and it is naming it as 5 or storing the number 5 in V. It is not storing the number 5 in B. It is storing 5 in some particular location and it is naming it as B.
Ma'am,
Ma'am,
Okay?
when we pass node, then it will store node at some particular location and name the whole node as v.
Exactly. If we are saying temp is equal to this particular node, then it means that it wants to rename the entire location of this particular node into the name temp. But there are multiple nodes involved here. There are multiple locations involved. One location will store the value v, the another location will store this none, the next variable. So there are two different variables in two different locations. So which one will it rename as temp? That's why what it is doing, it is just creating one more variable which is storing the location of this.
My second doubt is when in Python the memory is already allocated dynamically in Python list, then why we
Yes.
use linked list here? Because in other languages there is a limitation of memory allocation. Like
Yes.
in arrays, the memory doesn't allocate dynamically, so we use linked list. But in Python, the list is already a dynamic memory allocated object. Then why we use linked list here?
See, linked list is a type of data structure. What a data structure is, it is an abstract data type. This is kind of a data type. This is a definition of a new data type. Okay. So when in B++, when you are using a B plus tree, there is a linked list there. You are using a linked list over there. So does that mean like how are you going to implement that linked list? That is what we are learning here. That is, this is a generic definition of what a linked list data structure is. This is not some kind of a variable that we are discussing here. This is not some kind of a list variable or some kind of an array variable that we are discussing here. This is a generic data structure that we are discussing here. What it means? It is some kind of an overall definition. This looks like this. This does this function. I'm talking about a table. I'm not talking about my specific study table. I'm talking about a table. What a table is? It is some kind of a flat-like object. It contains four legs. That is all. And what we can do with it, we can just put it somewhere around the room and we can put stuff on that. We can keep things on that. We can study on that. We can do something on that. That's what we are discussing here.
Okay, ma'am. Got it.
Okay.
Thank you.
Yeah.
ma'am, just one time want to clarify. So when we
Yeah.
are calling node, it creates, I mean, it takes two memory locations and assign it value and next, right?
Yes.
Reference it as value and next, and then
Okay.
when inside the next we again call the node, it again creates another memory location and assign
Assigns two values to it.
yes,
Yes.
yes, okay,
Yes.
understood.
Yes.
In the next it is directly like storing the object itself instead of the location.
Ma'am, can you explain the problem step by step?
Sorry, even I don't know what the question is.
Ma'am,
I
can you
couldn't
please
understand.
run through the code once, ma'am? It's
What code?
ma'am that code written, it's
This
written here.
entire code.
Yes,
Ma'am,
This
ma'am.
entire code. Sorry, you want me to explain this entire code?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Please look into it. It's already 9:48, and there are a lot of other parts also that I need to cover. So you can look into it, and if you're having any doubts, then please go through this course.
Ma'am, this self dot is empty. Is empty? Is it a library function?
Yes, not isn't is not a library function. This is a function of the node class. Is empty is defined here. So when I'm using self here, it means whatever object is invoking that particular function. Okay, so self dot in is empty. Like suppose h1 is calling this append function, then it means that h1 dot append of v. Okay, so in h1 linked list we want to append the value v. So now my self is h1 itself because h1 has called the function append. So my h1 dot is empty means for the h1 function class. Sorry, for the h1 node, what is the called the isEmpty function. That is what we are doing here.
Right.
Okay. Please look into the details of the code. I will just explain the other concepts also. There are a lot of other concepts. Okay. So
Ma'am,
this is what, yeah,
in the class implementation self.next, we are directly
yes.
storing the next like object itself instead of the location, right?
I'm sorry, what?
No, in self.next, we are directly storing the next object itself. Like we are not just storing the its location. Like the
That
entire
is
node.
what we just That is what we were just discussing. Self.next is storing the memory location. Okay. Like we are creating one new object and we are storing the memory location of that particular object in this particular memory. In this next, we are assigning this value to this. I was explaining that using a v is equal to 5, right?
Yes, ma'am.
Yeah, that is what we were discussing just now, right? What exactly was your doubt? Is your doubt?
Okay, ma'am. So self.next is storing the location, the name, not
Yeah.
node.
Yes.
It is not storing
Yes.
the node.
Yes. Okay. So let's go to the next part. So now what happens here is in this linked list, what we did is we just created one node. Now this particular node is storing the information of the next node. This node is storing the information of the third node, and so on. We are doing this, right? Now, what happens if we put it in reverse also? We have a head over here, head pointer, which stores the starting of the node. Now, what we will do is, along with this information, I am creating one more location which will store the previous value of the previous node, the location of the previous node. Okay, I am calling this pointer as a tail pointer, which will store the last element of the linked list. Okay, the tail pointer will point to the node containing the last element. Okay, and there will be one more value instead of two values. Now I am going to have three variables in my node class. Okay, there will be three variables. One will have the actual value, the other will store the next value, which is basically the location of the next object, and there will be one more variable which is called as the previous, which is the pointer, and it will store the location of the object containing the previous element. Okay, if we keep on doing, if we have this kind of a definition where we will be having a previous pointer to point to a location which stores the element which has occurred previous to that element. Okay, in the friend example that we had discussed, every person is now having two cheats. One cheat will store the position where his next friend is sitting, and the other cheat will have the position where its previous friend is sitting. Okay, so this kind of a linked list is called as a double linked list, doubly linked list. The linked list where we just had the pointer referencing to the next friend only, it's called as a singly linked list. Okay, there was only one pointer which was pointing to the next element. Doubly linked list is we are having two pointers. One pointer points to the next element, and second element, the other pointer points to the previous element. Okay, and for doubly linked list, we have a head and we have a tail. There are two different pointers to refer to one particular linked list. Okay, so the head pointer will store the location, will point to the first node. Okay, the tail pointer will point to the last node. And singly linked list will have just one head. There will be just one pointer pointing to the next node, and there will be just one head pointer only. There is no requirement of a tail pointer. You can have a tail pointer, but it will be of no use to you. Okay. So this is about singly linked list and doubly linked list. This is
So,
the
ma'am,
representation. Yes.
hello.
Yes.
Yeah, now so data store in a between, like in mid. Yeah.
Sorry.
In W list, the data is stored in mid, na?
Yeah, the data is stored. This is a representation. There will be a data, there will be a previous, and there will be a next. Okay. The first element, previous value for the first element will be none. Next value for the last element will be none because there is nothing after this and there is nothing before this element. This, yeah, this element. Is this clear? W linked list.
Yes, ma'am.
What
Okay,
is the
great.
purpose of the tail, man? W linked list.
Tail will have the last element, so you can start from the tail. You can start from the last element and go back. If you want to go back, then in the singly linked list, if you want to read the list from last to the first, then what will you do? You start from the head, go to the 30, then you start from head, you go to 20, then you start from head and you go here and you come to 10, right? But if you are having a doubly linked list, you start from the tail, you read 30, then go to its previous, which is 20, then go to its previous and you get 10. That's the role of tail. Tail reads the list from the last. Okay?
Okay, ma'am.
Ma'am, in the class representation, yeah, in the below the
Yes.
code, there is no
Yeah.
separate concept of head. Just the first node itself is like acting as a head in this one. Yeah,
The first node is acting as a head.
yeah, there is no separate head here.
See, this is again coming back to the same thing that we discussed earlier. When I said this node of 10, no, what it does is node of 10, it means that it is creating a node here which is having the value 10 at its val position. Variable val will have the value 10 and next variable will store the value none. Now there is a head position. Now the head pointer, there will be a head. Now I'm just assigning the memory location of this particular node in this head. Now head is just storing the memory of this, so there is a head which is storing the memory of this. This is again coming back to what we have discussed earlier. Okay, we have a head here, we are just creating a head which will store the memory location of this particular node. That is what we are doing. Sorry, it will be pointed this way. Okay.
Yeah, okay. So the node 10 is acting as a head.
Yeah, the node is no longer acting as a head. There is a head variable which is storing the memory location of this node.
Okay.
Yeah, this is an object. Okay,
Okay, and head also has a value here.
head is
Okay, head doesn't have any value, it just as a pointer to node 10.
pointer to the node 10. Yes, exactly. This is something using two classes. You can look into this code. If you have any doubts, then you can post on Discourse. Okay. Then we'll go to stack. What stack is it is another kind of a data structure. Okay. But this is no longer a linear data structure. Okay. So what linear data structure is, we go one after another, right? It's not some kind of a linear kind of thing. So what stack does is, suppose you are given a bunch of coins, okay? So you keep all the coins one on top of another, right? And then when you remove, you just remove the first one. When you put one coin, you put on top of it. And when you need one coin, you just take the top coin and you go and use it, right? That is what is called as a stack. It is a list where you just put uh, everything like you have a bucket kind of thing, okay? When you get some very value, you put it into the stack, let's say V1, then you get the second value, you put on top of it, and then you get V3 and you put on top of it. Now you need to spend, let's say these are all 5 rupee coins. So you have the first 5 rupee coin, you get another 5 rupee coin, so you put on top of it, then you get another 5 rupee coin, you put on top of it, and you keep on doing this, right? But then now somebody you need to buy something and you have to pay 5 rupee coin. So you are not going to pull the last one. You're going to pull the top one, right? You have to pull out the top one, top 5 rupee coin which you have put it in the last, and you just use it to buy whatever you need. right? This kind of a structure is called as a stack. Okay, so you can use it, you can implement a stack using an array, using a linked list data structure, whatever you want. Okay, but the concept is this: what stack does is, when an element comes, when a value comes, you put it at the last, and when you want to remove it, you pull out the last number, right? So this put and this pulling out, this thing is called as push and pop. Okay, so what pushes? When you get some number, you push it into the bucket. And when you want to use some number, you want to remove a number, then you pull out the last element, and that's why it's called as pop. It just pops out the whatever is on the top. Okay, so that is the popping operation. Okay, so this is the last in, first out. Whatever comes last goes the first. Whenever you want to remove it, the first one to remove will be that particular number. Okay, this is what is called as a stack data structure. Then there is something called a queue data structure. It's basically QUEUE. Okay, um, QUEUE. Okay, this is a queue data structure. What this does is, it is basically very similar to what you experience in day-to-day life in a queue. So one person is there, is standing on the front of the queue. Then another person comes, stands behind him. Then another person comes, stands behind him, and this keeps on going on. And then when it's time to exit, the person standing at the front of the queue leaves. Okay, so whoever is at the front leaves the queue first. So first, whoever came first leaves the queue first. Okay, that's why it is called as first in and first out. Okay, so again, once again, you can implement this using a queue or using a linked list or an array or whatever you want. But the concept is, whichever entered the first should go the first, should be removed the first. Whenever you are inserting an element, it will be put in the last of the list. But whenever you are removing an element, the first element should be removed. Okay, when you are putting an element into the queue, it is called an enqueue operation. The name is just enqueue. And when you are removing an element from the queue, it is called as a dequeue operation. Okay, so now what are the applications and where can we see this stack and queue? Here we are given these applications of this. This is push pop. I discussed traverse displays. Basically, you can just traverse the stack and look into the different uh, numbers which are there in the stack. Similarly, for queue also, this is NQ and DQ we discussed. Then traverse displays basically to look into the list into the entire queue, whatever elements are there in the queue. So now there are some applications of stack here. What stack can help is, stack can actually be used to reverse a string or to calculate. So in computers, the algorithm to evaluate an expression, given a mathematical expression, you need to apply the Bodmas rule and stuff. No? So all of that expression evaluations come using the stacks, is performed using stats. Then there is something called DFS in graph, which you will see in later parts of the course. That is used. That is performed actually using stat. Reversing of a string. What you do, you find the last element and you put it in the first. Then you find the last element again and you put into the first, and stuff like that. Okay, so the reversing of a string is also performed using stat. And all of these are the different applications of stack. The undo redo operation, think about it. You are just doing something, doing something, doing something. When you perform an undo, the last operation is removed. Then when you are performing once again, you are performing an undo, the again the operation which was done second last is removed. But when you are performing a redo, the one which you have undone last is again redo, right? So all of these are applications of stack. And similarly, if you look into queue, it's basically job scheduling. There will be BFS, which will be discussed in the next week. Then there are these job scheduling operations, like suppose you are opening a calculator, you are opening a Chrome window, you are opening a solitary, and you are opening PowerPoint, you are opening multiple applications on your laptop, okay, or in mobile. You are opening WhatsApp, you're opening Facebook, you're opening Instagram, you're opening multiple things. So which one should be performed first, which one should be performed next? So the operating system itself decides that, right? So that particular, that operation, which one should be performed first, which one should be performed later, all of that scheduling is performed using queues. Okay, all of that implementation is done using queues. Okay, so these are the implementations of stacks and queues. You can look into that. Okay, any doubts?
Ma'am, what is spooling in printers? It was written.
Spooling in printers. Okay, yeah, I forgot to tell about this. Suppose you are like you want to print 10 documents. Okay, so what you do? You just go to the first document, Control P, enter. Go to the second document, Control P, enter. Go to the third document, Control P, enter, and so on. Okay, you did that. You gave like 10 PDFs you want to print. You just put Control P, enter. Like print all of these 10 PDFs. So now the printer, like you have to, like the printer has to perform one after another, right? So whatever has been given for to be printed first, the printer will print that first. Whatever will be printed second, the whatever document you have given print second in the second iteration, that will be printed secondly. Okay, so that sequencing, that thing is done using queues, right? So that is the spooling.
Okay, ma'am.
Okay. Yeah.
Ma'am, stack and queue are linked list or array?
You can implement them using a linked list. You can implement them using a array. You can also you can implement them as you want.
Okay,
Okay.
ma'am.
Like arrays. See, list is a data kind of a, like we are having an integer data structure and a float data structure, right? So, or when we are writing a value like five, we can implement it using an integer value, or as we can write it as an integer, or we can write it as a float, right? We can store
Yes.
the value when we write b is equal to 5. We can just write b equals to 5, or we can write b equals to 5.0. It depends on us, but the concept is same, right? So that is what
Yes,
here
ma'am.
we are having. We can use a stack. We can implement a stack or a queue, both using linked list or as an or using an array. It depends on our wish. Okay.
Okay, ma'am. Got it.
Okay. Then let's go to the next part, which is hashing. Okay. So this is kind of a dictionary to store a set of values. Okay. So what happens here is we want we have a bunch of values. Just give me a minute. Okay. So now I am giving you a list of numbers. Okay. Let's say 2, 3, 4, 8. Here there is 5. Okay. So here are 5 different numbers. Okay. So now when I'm giving this as an array, what it means, the computer understands that 5 should go to the 0th index. Okay. The 0th index will store the value 5. The first index will store the value 2. The element which comes the in the third occurrence, so go to the second index and will have the value 3. The element which comes fourth will go to the third index and will have the value 4. And the element which comes in the last, which is in the fifth position, will go to the fourth index, and hence 8 will come over here, right? So here we are using a function. What is the function? At whatever position the element is occurring, the index will be I minus 1. At the I minus 1 position, I will put that element, right? So that function is called a hash function. Okay, what is the function that we are using to store a list of elements in an array or whatever it is? In an array. Okay, in an array, we are having an index of we are having some indices, and we are getting a bunch of numbers. We want to store it in such a way that we are using some particular function to determine where this particular where this particular number will go. That is called as that particular function is called as the hash function. Suppose I say that no, I don't want to be stored it like this. I want to be stored at the second index, three will go in the third index and something like that. So then what will happen? I will need like 8 different indices. I will need 9 indices. Okay, 0, 1, 2, 3, then 4, then 5, then 6, then 7, and then I have 8. And 5 will come over here, 2 will come over here, 3 will come over here, 4, and then 8. Okay, this is my new hash function. This is what I'm saying, that my value will go to that particular index. Okay, so that is another hash function. Okay, so the hash function is basically I have I have a set of values and I want to put it in an array. Where should I put it in the array? Okay, that is what is called as a hash function. This is a very trivial hash functions, but then there are different types of hash functions also. So we'll look into that. What happens is with this hash function, the advantages is it improves on the time complexity for very basic operations like insertion, deletion, and something like that. But not on smaller data sets. Like if you are having 10 or 5 numbers, it will not affect something. But if you are having numbers in millions, okay, then hash function comes into real usage. But see, suppose I am having, like I said that if you look into this particular example, see what happens. I had the number till 8, right? If I go with this particular hash function, I want this to be stored in that particular index. That is what my requirement is. But if I have 1 million over here, the sixth number will be 1 million. Then what will happen? This particular list will keep on increasing. It will go on increasing, right? So this is a very bad hash function. This list will have a space complexity of like 1 million. It needs 1 million indices to store this 1 billion value, right? So as compared to this particular thing, this is a better hash function, right? As compared to this hash function. So that is the concept of hash functions. If we are having very large number of values, we want to store that large number of values in a smaller sized data structure, smaller sized array. Okay, and that is why we are going to use some kind of a function, a mathematical function, to map each of these numbers to its particular index. Like suppose I'm having this 1 million numbers and I'm going to use, I am having just 6 numbers, 6 values are there, and one of them is 1 million. So instead of using this, I can use this. This is an option. I agree to that. But what if I use something like this also? The function I'm defining it as, the element will go to the index such that this element v modulo of 10 is equal to whatever will be the number here at that particular index I'll put. So when I find 5 modulo 10, it will become 5. So I will put 5 in the fifth index. Okay, then 2 will go to the second index. 3 goes to the third index, 4 goes to the fourth index, 8 goes to the eighth index. Okay. And at the zeroth index, I will have my 1 million. So I actually have this 1 million. I can accommodate 1 million, but all I need is an array of length 10. Right? So I can accommodate up to 10 values. I can have store like 10 different values, but I can store values up to 1 million. Okay, here we don't have any extra space, right? I mean, it's a vector, I agree with you, but this is actually what I'm saying is this is a kind of a function. This is a data structure, not a data structure. This is a function that is used to map these values. Okay, this is also a hash function. I agree with you. This is also a hash function, but here we can store 10 different numbers. I can accommodate more numbers also if it comes. Here, yes, I can accommodate if I consider this as a vector. But here we are just looking into arrays. So arrays are usually of fixed length. Okay. So we are defining this is a data structure kind of a thing. Okay, this is a generic concept used for arrays. So when we are having very large possibility of getting larger numbers, and we need to accommodate them in a smaller space, then we are going to use hash functions. Is this
Ma'am,
clear?
one thing.
Yeah.
Yeah, ma'am. One thing you just told, right? Like, we'll, for example, we use a function that is v mod 10, and the modulus function, I mean, the answer we get, we store value at that position, right?
Yes.
Suppose we want to store 5 and 15, so both will get the same position mapped by the function.
That I will come next. That's coming next.
Okay.
That is called collisions. Okay, we will come to that next.
Okay, ma'am.
Okay. So just like he said now, that is called as collision. Such scenarios are called as collision. Suppose I want to store 15 now, and I'm using this particular hash function. So now 15 should also go to 5 at this particular position, but that is already occupied. So now where should I put 15? Okay, so now there are different types of has like this is called as collision resolving technique. Okay, there are different types of collision resolving techniques. Okay, so one of them is called open addressing, and the other is called closed addressing. Okay, so what we'll just discuss closed addressing first because it is a little bit easier. I feel it is little bit easier as compared to open addressing. So what closed addressing does is instead of storing one value, I will have a place for one linked list over here. This is an array, okay? But each element of the array will store a linked list, okay? So here I will store a linked list. The first element of the linked list will be 5. The second element of the linked list will now be 15. Now when 25 comes, I can again put in another element over here and I can accommodate 25 over here. Okay, this is what is called as closed addressing. Or we can just use one array in each of these particular uh, uh, array of arrays, kind of a matrix kind of a thing. We can have a matrix. We have a matrix over here. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is my these are my rows now. So now earlier I had 5. So in that 5 for this fifth row, I had the first value as my 5. Then when 15 comes, I put in the second row, second column. Okay, for 5. Okay, second column of 5 will contain 15 now. The third column of 5 will now contain 25 when 25 arrives. Okay, and so on. This is possible. That is what is called as a closed addressing. Okay, so now there is something else called as open addressing. What open addressing does is we will use another function, or we will just modify this function little bit. In case of it is a collision, what I'll do is I'll just find the next consecutive position where it is available and I'll put it over there. Okay, so what I do is I go to when I encounter 15, I say that hey, 15 is here. It is colliding at this particular position. It is already occupied. So what do I do now? You imagine like you are going to a theater or something. You don't have like an exact reservation. They are telling you that this particular row anywhere you can sit. So this particular you can sit anywhere, and you are just going to your favorite seat, but it is already occupied. So what do? You just find a seat next to it, right? That is exactly what open addressing is here. Open addressing is, so here what we do is, sorry, yeah, one second, sorry. Yeah, so what open addressing is here? So we find a position which is empty. If this particular position is closed, is occupied and it is colliding at this particular position, we are going to find the position which is empty and we will occupy that particular position. We will go to our next favorite position. Okay, let's say my next favorite position is I will do V mod 3 and I will find that. First of all, I will perform V mod 10. If it is colliding, I will do V mod 9. Now V mod 9, sorry, V mod 3. Okay, what V mod 3 will give me? V mod 3 will give me 0. But that is also occupied. Then I will go to third rule. Third rule is my V mod 2. V mod 2 is equal to 1. Okay, so now 1, this is empty. Okay, yeah, this is my third favorite position. The first two favorite positions are already occupied. So I'll just occupy here. That is what is called as the open addressing technique. Okay, so the way we choose our favorite places, that is called as probing. Okay, so there can be different types of probing. One is called as linear probing, wherein we just linearly counter, linearly update. Okay, we start from 5. So our first favorite position is V mod 10. So I go to V mod 10 for 15 is 5, and I see that it is already occupied. So I'll just go to the next seat, which is 6. Hey, 6 is empty now. So I'll just occupy 6. Now when 25 comes, it goes to its favorite seat, which is V mod 10, and that is 5, fifth position. It says that, okay, this is all occupied. So then let's go to the next consecutive seat, which is 15. Okay, yeah, this is also occupied by 15. So, sorry, it's the sixth position and it is occupied by 15. Okay, so now I am sad a little bit, but my third favorite position is available, which is the seventh position. So I'll just occupy over here. Okay, this is what is called as linear probing. It is not necessary that you will increment by exactly by 1. You may increment it by 2. You may increment by 3 or something like that. You may increment as you depend on. Okay, so you like here you can we have HK. So here what is happening? My hash function is defined as h of k plus I modulo m. Here m is my 10, okay? And I will keep on incrementing. I will start from 0. I start from 0. I see that the 0, when I become 0, what it happens? My first choice is V mod 10, right? So here I go to the V mod 10. It is occupied. Then what I do? My second choice is V plus 1 mod 10, which will give me the sixth position, which is basically the consecutive position. This is basically equal to V mod 10 plus 1, right? Then
Yeah.
the third one will be V plus 2 mod 10, my third choice, which will be basically V mod 10 plus 2. Okay, and so
Yes.
on, right? So this is my hash function now. A generic function to define all of my favorite choices, the sequence of my favorite choices. Okay, so this is called as this is my hash function. Okay, so this is here I instead of like having plus 1, I can just increment by 2. So after V, I will start with V plus 2, or then I will start with V plus 4. Then I'll go to V plus 6. Then I'll go to V plus 8, and so on. I can just do whatever I want, right? So that is what on what basis, or what exactly we are defining. What is the sequence of choices that we are having? That generic function for that is called as a hash function.
And ma'am,
Yes.
if I want to insert at 15 at the first index, then how it is possible, ma'am?
At the
15 or
first index.
yes, ma'am.
See, that depends on what kind of that depends on what kind of hash function we are using. We need to define. Let's say I'm just going to define a hash function such that my hash function will be something like that. If the number is 15, if v is equal to 15, then insert at 1. Okay. Otherwise, insert anywhere you want except 1. This is also a valid hash function. That's all I'm saying. All I'm saying is that there is some kind of a function that we are following to insert these values.
Okay,
Okay.
ma'am.
So there is another way also. Here, instead of like linearly increasing the value of I, instead of like saying that I will increment by 1, if I keep on increment square, like first of all I'll go with 1, then sorry, first of all I'll go with 2, then I go to 2 square, which is 4, then I go to 4 square, which is 16, then I go to 16 square or something like that. Okay, if I keep on squaring it, or if I keep on using an I squared function over here. First of all, I will have I squared, which is 1 squared. Then I will have 2 squared. Then I'll have 3 squared. Then I'll have 4 squared. Something like this. That is also allowed. Okay. So this here, what happens? My function, these values of I is increasing. Initially, when I had h of k plus I, my value of I was increasing linearly. Now what is happening? My value of I is increasing on a quadratic function. So it is called quadratic probing. Okay. Here, when I was increasing I as 1, 2, 2, 2 to the power 0, then 2 to the power 1, then 2 to the power 2, then 2 to the power 3, then this is exponential probing. Okay, so this is different ways of probing. Okay, when I'm increasing, what probing means, what is, you just keep on checking where you can find probing, like you take a needle and you keep on putting it, inserting until you find a hole. That is called as a probing, right? So here linear probing is something like that. We just keep probing until we find a available position. If my eye is increasing linearly, then it is called linear probing. If my I is increasing on a quadratic function, it is called quadratic probing, and so on. That is what is called as open addressing. Is this clear or any doubts?
So, ma'am, this hashing is used for faster, I mean, like searching or insertion, right?
Yes.
So, if we, I mean, use this list kind of method, so wouldn't it take a longer time?
See, that is the concept here. Okay, hashing is mostly used for very, very large data sets. When you are having your values can go to millions, but you are having just 10 or 15 values. So what you have to do is you just have to store this 10 or 15 values, and you need to just look into this 10 or 15 values. You don't need to look into this 1 million values to just search for a number or to search for whatever you're searching for. Okay, so instead of like storing 1 million values in one particular array, hashing is a way to compress this array into a smaller array of size 10 or 15 or 20 or whatever it is, your bucket size
But
that you are defining.
yeah, ma'am. But for like closed addressing, as you said, we have to uh, make a linked list for each position which is already covered. So we keep creating a linked list. So for finding a value there, wouldn't it take like O of n to search in the linked list?
Why will it take over from? Oh,
If
okay,
we are
yeah, sure. Yeah, it can take off and but sorry, give me a minute. Sorry. Yeah, it can definitely take O of n, but see, it depends on the application purposes. When you are having uh, like hundreds of numbers, but you are your number can go up to 100, but the numbers are limited to like something about 10 or 15 values, but some of them are very, very similar. You are having only 100 students, and you are grouping them into 10 different groups, or based on the number of clubs you are having. You are having 5 clubs, and you are grouping all of these 100 students into these 5 clubs. Then you should go with closed addressing, right? Instead of open
yes,
addressing. But if you
yeah.
are having like the previous example that I gave, you're mapping these different star positions. Okay, your positions can go up to millions, but what you are noticing in this one particular small space, that is very limited. Okay, so in this
Okay.
small, very small, you are having a very few number of elements, but the values are very large. And you should go for open address. It depends on the, it actually depends on the application you are using. These are different types of, these are the different types of hash functions. These are different ways to address the collisions. Okay, it depends on you
Okay,
which
ma'am.
one you use depending on your application. Okay,
Okay. So for the open addressing, uh,
yes.
we don't have to traverse through whole list, but we have just a function which we have to apply the values, and whatever we get as answer, we just point to that value, right?
Exactly. Yeah. We
Okay.
like for example, suppose we are having 20 numbers and you want to search for a value, let's say 25. We are using say v mod 20 as my some as my hash function. This particular function where m is equal to 20. Okay. So what can we do? We can just start with we will if we are looking for some particular we start with v mod 20. Is it present in this location? No, it is not there. Then just go to the next location, then go to the next location, then go to the third location, and so on. This
Okay.
somewhere you will find it. The worst case will be order of n. I agree. But it is
Yeah.
also the best case will be order of 1. That is
Yes,
also
ma'am. Got it.
Now we can use closed hashing when the array where we are storing these hash values is larger
there.
than the original array, right? Then we can use closed hashing.
Yeah. If the
If the hashing array, like the array where we store the hash values, if that is larger than the original list, then we can use
okay.
closed hashing.
If the array where you are storing the values
The
is
hash,
larger,
like if we have more space in the hash value, like hash
yeah,
array, then we can use
yeah,
closed hashing.
yes, definitely. Yes, definitely you can use. But see, suppose your array is having like your original, there are 15 numbers, okay? Now you cannot put these 15 numbers in an array of length 5 using closed hashing.
Yeah, then we need open.
Then you need to go for open hashing. Okay? It depends on the application that you're using. Okay? Any doubts or questions? Hello?
No, ma'am. No doubt.
No,
Okay.
ma'am.
Okay, if you don't have any doubts or if you face any doubts in during the course, during like in this week or anything, then please post on Discourse. And if there are no doubts, then you may exit. Yes,
Ma'am,
Prashant.
can you could you please show that class representation for linked list, the code please? I have
Okay,
one
one
doubt.
minute. One minute. Let me be sure.
Like the append function.
Here, yeah.
Yes, but initially, like first we are if we are referring to that linked list, we
Okay.
always refer to the head, right?
When you're
Like
referring to the
linked list, we refer it using the head. Right?
yes, the head. Yes.
Like so, then we'll use head dot append v, right, to invoke this function.
Yes. Yes.
Then the self will be head, right? Head is the
Yes.
self.
Yes.
Then
Yes.
self will be empty, right? Like self dot value will be
No, see, self
empty.
is basically saying I. Self is a way in these programming languages, self is a way to represent me, I. Okay? Hi, I. I want to append the value V. That is it is kind of a keyword. It is a keyword. You can't use it as a variable or anything. Okay? It is a special kind of a variable which just shows me, hello, me, it's me. And what I want to do, I am here to append the value v. That's what self is doing. So when we write head dot
Append. Yeah.
append v, what it does is it is calling this function v, this function append self comma v. Okay. So now what self is does? Self is doing hello, it's me. So I want to append the value v. So what is who is this me? The me is head here. Who is this? Who is saying this to this append function? The head is saying that. Okay, so what this means is when I am calling this function, it means that the head is telling to the append function, hey, I just want to append the value v. The self means that. Okay, so self is basically a very special kind of a thing defined in Python. See, what is none? None is a special keyword which just shows that it is nothing. It is basically nothing. It is not zero. It doesn't have the value minus infinity. It doesn't have the value plus infinity. It doesn't have the value zero also. It just basically means that it is nothing. Right? It is nothing. Just like that, self is a special kind of a keyword which means that it is me. Whoever has called this function, it's me. Hello, it's me. Okay? You don't have to worry about somebody else. It's just me. I want to do this. So I want to perform this function.
So self is not ed. It is not ed.
This is not a variable. Self is not a variable. Self is just some kind of a keyword. It is a special kind of a keyword which says that hello, it's me. I want to perform this particular function. And who is this me? The person who has called that function, who is using that function.
Okay, ma'am. So then in the first if condition, if self dot is empty, it will check the first value, the pointer of
Yeah,
it,
it
right?
will exactly. It will check the pointer value for head. Whatever the head is having. So what will happen? What will happen here? It will call the isEmpty function for the head. Okay, head dot. It is basically head dot isEmpty.
Yes, ma'am. But it is not storing any value. It is only storing
Yeah,
next pointer.
that is a different thing. That is a different thing. IsEmpty is a function. There is a definition for isEmpty here. It will call this function.
Yes,
Self
ma'am.
dot isEmpty means it will go and call this particular function.
Yeah. Then what will happen?
Then it will check here. Self dot value is equal to none. It will check if the value of stored in this particular location, okay, whatever head is storing, is the value none. If it is true, then just return true. If it is not true, then it will return false. That's like that.
Yes, ma'am.
So what head is storing? Head is basically storing this particular node, right? This node can have some value v or some value none, right?
Yes.
Otherwise, head is basically storing the value none. Right? So when I'm calling this is empty, when head is calling this is empty, what will it do? It will check for its value. If the value is not none, that means there is some kind of a node is there. It is not an empty linked list. So it will just return false. But if there is no value there, if the value is none here, then it will just return true. That's it.
Ma'am,
So ed
Yeah.
dot value will refer to the pointer.
Yeah, the pointer, the
So self
location.
dot value will have this week and next this node.
Yeah. Yes.
Then it is not none.
Yeah, if there is a node, then it is not none. But if there is no node, if it is empty, then it will be none.
Yes, ma'am.
Yeah, somebody else said it out.
yes, ma'am. Ma'am, in the if self is empty, there is no value inside the parentheses. I'm so,
I'm sorry.
ma'am, in the line 14, like if self dot is empty, there is no value inside the like parentheses. So why it is not there, ma'am? Ma'am, in the line 14.
Yeah, that's what I'm saying. The isEmpty function, the only value for isEmpty is self. Self is a keyword. It's not a variable. Self means it's me, whoever is calling. That's all. Who can call this function? Self can call this function. Who is this self? Self is that person who is calling that function. It means that is empty of self means is empty of self means um, it means that whoever is calling this function, it just has to write, hey, I am calling the isempty function. It doesn't take any arguments here. There are no parameters, there are no arguments. Self is just a keyword which refers to the person who is calling this or to the basically to the object who is calling this particular function. There are no, self is not a keyword, it's not a variable. Okay, that's why we don't have any function, anything within the parenthesis. Within parenthesis, whenever you are calling a function within the parenthesis, only the arguments or the values for the parameters can go. You can't just put anything over here. Only whatever the arguments the function requires, those things will go in over here. Self is not an argument.
So self is the class object like on which the
Self
function
is
is called.
exactly self is the class object who is calling that function. It just denotes that. It is a keyword which denotes that.
So, ma'am, if it has some other value, not self, then like including self, then we need to pass the argument inside at the 14th line of the
Exactly.
code.
That is what happened for append here. That is what happened here. Append of self comma v. The function has been written as append of self comma v. So when we are calling the append function, who will call the append function? An object of this class node can only call this append function. Okay. So that object will call it as head or whatever the name of the object is. Let's say the name of the object is obj dot append. And what are the parameters of this append function? B. So it will be B. That's all. Or 5 or whatever. The value for the variable B.
Yes, ma'am. So, like, if we call head dot append, then it will check if self dot is empty. Like, if the head is pointing to another node,
Yeah.
then it will not pass the first if condition. Then it will go
No,
to the
that node will not be
else condition.
passed. No, yeah, exactly.
Then it will check for head dot like self is head, right? So
Yeah, that is what I'm
dot
saying. You
next.
are right. You are right. Yes. Self is head. It is not going to do anything else. Self means the object which is calling that particular function. That one.
Ma'am, so cell head dot next and head dot value both will contain the next node V.
No, this is for the current node. No, if the current node is empty, it is checking which node is empty. Head is not empty, right? If head is empty, then what is happening is a different thing. It's an append function. Append function means you are not having an empty node. You are not having an empty list. Append means you are just appending at the end. You are adding something at the end. That is an append function. It is making sure you can only use the append function when you know that the list is not empty. You get it?
Yes, ma'am. Then when we call head dot append, then like for the first if condition self dot is empty, it
It
will
will be
check
false.
head dot value. Right? But in head we don't store any value. We only store the pointer. Then what will be head dot value? Like this first.
See, head dot value stores the pointer to what?
No, ma'am, head dot next only shows the pointer, right? Head dot value is
Head
none.
dot next doesn't store the pointer. Head is itself a pointer. Head is the pointer to the node. Head is not head is not a class object. Head is a pointer to this node. Okay, head stores the memory. That only we have discussed earlier. Okay, so we have a node whose memory location is something AX000F. Okay, then what head will store? Head will be a variable which store this value AX000F.
Ma'am, had is temporary created, no? Like
Head is not temporarily created. Head is created. Below here. That is printed over here. This is the value 10. This is the explanation for this.
Yes, ma'am. Yes.
So, like to summarize, head dot append will check if head is empty.
Exactly. If head is empty, if this location is empty or not.
Okay, then it is not like if it has a pointer, then it is not empty. Then can
Exactly.
like what will happen in the second else condition? Elif in the code, can you show me? Yeah, yes. Here,
Here.
if self dot is empty, we will not enter it because it is having a pointer. Then it
Yeah.
will check for the elif else if no above.
Yeah.
Now definition append. Elif self dot next equal to none, it will check.
Okay, then I believe. Wait. What is happening here? Head is equal to node of 10. So what will happen? Okay. Then you were right, I was wrong. It's just naming this first node as head. Okay, you were right, I was wrong. Okay, so this is head. So now it is checking if it is empty or not. And if it is not empty, and it is, this is clear, right? This, if
Yes.
this happens, this is clear, right?
Okay, the first node itself is acting like head.
Yeah,
Yeah, now it's clear. Yes.
now it's clear, right? Okay, so
Yes.
the explanation that I was giving you earlier, that was not wrong also. Okay, when you look into C, when you look into the pointers concept of C, that is what the explanation was. Okay, so we have a head variable which stores the memory location of this particular uh, node. Okay, but in Python, everything is on this reference pointers basis. So let's not go into all of that concepts and confuse a lot more. Let's just go with this particular notation. Okay.
Okay, and this class implementation is just one of the implementation of linked list.
Yes, this is an implementation context.
Okay,
If you
okay,
have any other implementation, go ahead. You can do that. Okay.
okay.
But not when in an examination you are given that you have to use a class implementation, then you have to use a class implementation. Okay. But if you
Yes.
are given some, you just want to explore on your own, then please go ahead with any implementation.
Yeah, okay.
Okay.
Thank you.
Excuse me, ma'am.
Yes.
Ma'am, I have a small doubt. Can you please take that?
Yeah. What?
Ma'am, in the lectures, I was saying that if you want to exchange like two elements, then it will take the constant time for the arrays and the order of n for the list.
Yes.
Can you explain that? And the same with the delete and the insert versus like constant time for the list, like it was just opposite. Like for the delete and the
Okay.
insert, it was the
See.
constant time for the
See.
list. And
Okay. What happens? You know the position I and the position j, right? For the both of these elements.
yes,
All you have to do is take this very value. How do you swap in the array, in this list or an array, whatever it is? How do you swap these elements? You take a temporary variable, store a of I. Let's say this is a, okay, the array. Then a of I is equal to a of j. Then a of j is equal to 10, right? This is what the swapping operation is for arrays, right?
yes, ma'am. We can also do like a of a of I comma a of j is equal to a of j comma a of I.
Yeah, this is the detailed explanation of that particular statement. This is a breakdown of that particular statement. That's what I'm saying,
Okay, ma'am.
right? That
Yes, ma'am.
all you have to do is a of I, comma a of j is equal to a of j, comma a of I, right?
Yes,
So this
ma'am.
is constant operation. You agree to that?
Okay, ma'am.
Do you agree to this?
Ma'am, can you elaborate it, ma'am?
Sorry?
Can you explain it, ma'am?
Explain what?
Like the constant time.
The
Okay, it
constant
will.
time is
Yes, ma'am. I got it. It will be the swapping. Yeah.
This is a swapping, right? It is constant
Yes,
time,
ma'am.
right?
Yes,
Okay.
ma'am. Yes, ma'am.
So now let's go to a linked list. Okay. So in a linked list, what we have, this is the ith node. Okay. Containing the value a of I, and then here we have the jth node containing the value a of j, right? And then we have something else also. How do you perform the swapping operation here? How will you perform the swapping operation? There is a node here. There is a node here. There is a node here. How will you perform the swapping operation here?
Mm, mm.
First of all, you need two pointers to locate these two particular locations, right? And for that, you need to search that entire list, right? Do you
Yes,
agree
ma'am.
to that? In fact, you don't need to point to this particular location. You need to point to this particular location, the previous location, previous node, right? You know, need this is previous of I, this is previous of J. I'm naming these two nodes as P of I and Pj. Okay. So now what I need to do, I have to remove this particular node from here and I need to put it over here, and I need to remove this node from here and I need to put it over here, right? So I have to change this particular uh, pointer to here, the next pointer from here to here, change this particular pointer, the next pointer from here to here, change this next pointer from here to here, and the next of this will come to here. All of these operations will be done. All of that operation will be unit amount of time. But if you are just asked to swap I and j in arrays, you can just go to the ith index directly. You can just go to the jth index directly. But in the linked list, to find the ith index and the jth index, you have to scan the entire list.
Yes, ma'am. Got it, ma'am.
Okay.
So for array it will be order one, and for linked list it will be order n, right? The swap operation.
Exactly. Yeah.
And similarly for append also, right? Append for array will take order one, and for linked list it will be order n.
Exactly, because in array you already know the length of the list, right? So all you have to just do is like a of n plus a of like list dot append function. What it will do is it will basically add a of n is equal to whatever value you give. But here what you have to do in a single linked list, you have to go till the last. You have to find which one of these is the last element. You have to scan the entire list to find the last element, and then you put in your add your new value.
But if you have a tail, it will be easy.
Yeah, that is a doubly linked list scenario. I'm talking about a single linked list. The time complexities vary, right? If you want to insert an element, okay, at the head of the list here, if you want to insert an element at the head, what will happen? In single linked list, it is order of 1. In double linked list, it is order of 1. If you want to insert at the tail, then in single linked list, it is order of n. In double linked list, it will be order of 1. So there are different time complexities. You need to look into that. You need to explore that. Okay?
Yes, ma'am.
Ma'am, but for insert, it will be the order of n always, like for the deleting and for the inserting.
Why? For inserting at the head position, at the start of the list, why will it be order of n?
For the arrays, ma'am.
For arrays,
Yes, ma'am.
you have this thing, no? A of in the list representations, A of one column will be insertion at the start will be order of n. Insertion at the end, if you are going with Python, let's just go with Python. In Python, it actually can be done in order of one. But if you are going into arrays in C or C++, it will be order of n for both the scenarios, right? Actually, it will be order of n for the end of the list. Oh, sorry. start of the list, and it will be order of 1 for the end of the list, if you know the length of the list, right?
In Python list.
In C and C++. In C you have an array, in C++ you have an array, okay? But then, let's say this array is of length 100, you have 5 elements, okay? And when you are going to, you know that there are 5 elements in the list. If you are inserting one new element, okay, you don't know 5 elements, or if you know 5 elements are there, then you just need to insert at the 6th element, right? So it will be order of 1. But if you want to insert at the start of the list, then what you have to do is you have to copy every element to its next element, and then you will have to insert at the start. But in Python, you can just write a of 1 colon equals to a of 0 colon, and a of 0 is equal to b, and it's done. This is the unit time operation. See, the time complexity depends on what is your code, what is your algorithm, what is the programming language. There are different factors on which the time complexity depends. Okay, so you need to come look into the algorithms. You need to explore the algorithms to understand the time complexity of a particular algorithm. It also varies from implementation to implementation. Okay, if in some implementation you are using some kind of an intelligent, smart kind of checkups, and you finish it in like one particular in order of one, then well and good, go ahead. Okay, any doubts, or is this clear? Hello,
No, it is clear.
hello.
No doubt.
Okay,
Thank you.
thank you.
Thank you, ma'am.
Thank you,
Thank
ma'am.
you. Thank you. Okay, in that case, I'm stopping the streaming and the recording.
Yeah, ma'am.
Okay.